Hello, and welcome to Night Cosmos Sleep. Thank you for taking the time to stay with us on a slow, quiet, and curiosity-filled journey through the universe. Tonight, we will turn our attention toward a planet once seen as a symbol of beauty in the sky, yet behind its brilliant light lies a very different secret. It is a world astonishingly close to Earth, familiar to people in ancient times, but the more deeply it has been explored, the more clearly humanity has come to understand that beauty is sometimes only the first veil concealing something deeper. Take a moment to relax and let the story of Venus unfold slowly without hurry, without noise, like a distant light gradually revealing what it has kept hidden for billions of years. We will begin this journey not with the thunderous sound of a rocket, nor with dramatic images of volcanic craters or storms moving through space. We will begin with a very small and familiar point of light, sometimes resting quietly at the edge of twilight, sometimes appearing before dawn has fully opened its eyes. At some point in your life, you may have seen it, a light so bright that it is difficult to ignore, steady against a sky slowly changing color, like a tiny piece of brightness carefully placed within the quiet boundary between day and night. People in the ancient world gave it several gentle names. When it appeared in the morning before the sun rose, it was called the morning star. When it appeared in the evening shortly after sunset, it became the evening star. Those two names sound almost like two different faces of the same light, one announcing the beginning of a new day, the other watching the old day fade away. But that bright point is not actually a star. It does not burn with its own light as the sun does. Nor is it so distant that its light must travel for years before reaching us. It is a planet, one of Earth's neighbors in the inner solar system. It is Venus. From the ground, Venus looks remarkably peaceful. It does not twinkle as strongly as distant stars often do. Instead, its light usually appears steady, full, and certain. On clear evenings, while pale orange still lingers in the sky and the lights of buildings begin to turn on, Venus may appear like a silver pin pressed into the open air. On quiet mornings, while the air remains cool and the streets have not fully awakened, it stands there as a small sign that darkness will soon begin to retreat. Its presence feels so familiar that it is easy to forget we are looking at another world, a real planet, moving around the sun along its own orbit, wrapped in its own atmosphere, and carrying a story completely different from what its outward light seems to suggest. Venus is the second planet from the Sunday. It lies closer to the sun than Earth does, though not as close as Mercury. At many times, it is one of the brightest objects visible in our sky, surpassed in prominence only by the sun and the moon. Its brilliance makes it one of the easiest planets to recognize with the naked eye. No large telescope is required. No complicated equipment is needed. With a clear enough sky, the right moment, and a little attention, anyone may encounter Venus standing near the horizon, like a familiar presence. Yet that very visibility creates a misleading impression. When something appears beautiful, bright, and peaceful from far away, we often give it a sense of gentleness. We may assume that a soft point of light in the sky must belong to an equally gentle world. We may imagine that its brilliance comes from clarity, from bright and beautiful landscapes, or from an atmosphere resembling Earth's white clouds. But Venus is not bright because it is peaceful. It shines because it is completely covered by a dense layer of clouds, a veil that reflects sunlight with remarkable strength. Those clouds act like a hazy mirror surrounding the entire planet, sending sunlight back into space and making Venus appear radiant from Earth. The strange thing is that the source of this beauty is also what conceals the truth below. When sunlight reaches Venus, much of it does not travel directly to the surface. It encounters thick layers of cloud, where it is reflected, scattered, and held within a misty world of yellow and white. From Earth, we see only this outer covering. Even through an optical telescope, Venus does not reveal distinct regions of land as Mars does. It shows no continents, oceans, or familiar outlines like those visible on Earth. It resembles a glowing sphere wrapped tightly in a veil, quietly beautiful, yet almost unwilling to let anyone see inside. There is something deeply human in the way we have looked at Venus. From a distance, we gave it gentle names: the morning star, the evening star, the star of dawn, the star of twilight. But the closer we came through science, through spacecraft, radar waves, and measurements of temperature and pressure, the more we realized that this light was not an invitation to descend. Beneath the brilliant clouds lies a world hotter than Mercury, even though Mercury orbits closer to the Sun. Its atmosphere is so heavy that it can crush machinery. The air is not the gentle mixture we breathe, but is made mostly of dense carbon dioxide. Its clouds are not ordinary water clouds, but contain tiny droplets of sulfuric acid. There are no ocean waves on the surface, no grass, no trees casting shadows, and no soft rain reaching the ground. It is a hidden landscape, intensely heated and held within conditions so severe that they seem almost completely opposite to the beauty we see from Earth. Venus is therefore one of the deepest paradoxes in the solar system. From far away, it is among the most beautiful planets. Up close, it is also among the most terrifying places. It is Earth's neighbor, yet it is not a place where a human being could simply stand and look upward at the sky. It is similar in size to Earth. Both are rocky planets, and both formed in the inner region around the young Sun. Yet their histories followed very different paths. From the very beginning of this journey, Venus presents a quiet question. How could a world that appears so gentle conceal a reality so extreme? That question does not need to be answered quickly. With Venus, the truth must almost be uncovered one layer at a time. First comes the light we see from Earth, then the reflective clouds that make the planet shine. Beneath them lies an atmosphere as deep and heavy as an invisible ocean. Farther down are the heat, the pressure, the rocky ground, the volcanoes, the uncertain signs of geological activity, and an ancient past that scientists still do not completely understand. Venus may once have been different. It may once have possessed water and a climate less severe than the one it has today. Or it may have begun moving toward heat and dryness very early in its history. These questions remain open, and that uncertainty makes Venus more than a beautiful sight in the sky. It makes it one of the greatest mysteries located close to our own world. Throughout the history of human observation, Venus has often appeared during moments of transition. It becomes visible before the day has fully begun, or before the night has completely arrived. It stands along the boundary between light and darkness, waking and sleeping, the clarity of daytime and the stillness of night. Perhaps this is why it settles so easily into memory. A child may wonder why such a bright star is visible before the sky is fully dark. Someone returning home late may notice it between power lines and rooftops. Someone awake before dawn may see it outside a window before the city begins to move. Venus does not enter human experience as something completely unfamiliar, but through a soft and familiar presence. Science sometimes begins with that very sense of familiarity. We see a bright point and ask what it is. We learn that it is a planet and ask why it shines. We discover that the brightness comes from clouds and then wonder what those clouds are hiding. In this way, a single point in the sky opens into an entire world. And that world does more than teach us about Venus. It also causes us to look at Earth with a different feeling. If two planets can lie so close together, share several basic characteristics, and yet become such profoundly different places, then Earth's calm and habitability no longer seem inevitable. Tonight, as we begin entering the story of Venus, there is no need to carry a sense of fear. All we need to keep is a slow and gentle curiosity. Let that bright point appear before us as it has throughout human history. Silent, radiant, familiar, yet never simple. From here, we will move closer little by little, not to destroy the beauty of Venus, but to understand why that beauty exists, and why behind it lies one of the deepest lessons about atmospheres, temperature, water, and the fate of a planet. From a beautiful point of light seen from Earth, the journey begins to unfold. And the closer we move toward Venus, the more clearly we realize that its beauty does not come from gentleness, but from a veil too thick for human eyes to see through. Beneath that veil, another world is waiting for its story to be told slowly, quietly, and brilliantly, in a way completely unlike anything we once imagined. Once that bright point is no longer merely a dot in the sky, but is called by its true name, Venus begins to feel closer. Not close in the sense that human beings could simply walk toward it, nor close like a familiar place on a map. It is close in the way a neighbor is always there, moving beside us within the sun's vast neighborhood for billions of years, sometimes drawing nearer, sometimes moving farther away, but never truly leaving Earth's story. What makes Venus special is not only its brilliant appearance. If it were merely a beautiful planet in the sky, perhaps the story would end with admiration. But when human beings began measuring its mass, diameter, structure, and position within the solar system, something remarkable became clear. Venus resembles Earth more closely than many other planets do. It is not like the enormous gas-filled Jupiter, nor Saturn with its broad rings, nor Mars, which is smaller, colder, and dry in a different way. Venus is a rocky planet. It has a solid body, a core, a mantle, and a rocky crust. Its size is so close to Earth's that for a long time, people have called it our planet's twin sister. When their basic numbers are placed side by side, that similarity becomes even clearer. Venus has a diameter of about 12,104 kilometers, only slightly smaller than Earth. Its mass is also not dramatically different from Earth's. Both planets formed from rock and metal in the inner solar system, where worlds could not retain the enormous layers of gas surrounding Jupiter and Saturn. Both are rocky spheres, orbiting the Sun, receiving light, holding heat, and being shaped by volcanoes, atmospheres, and time. By the most basic measures, Venus seems almost like a nearby version of Earth, but similarity in outward form never guarantees similarity in fate. Two people may be born in the same home and grow beneath the same sky, yet a few small differences, extended over many years, can send their lives in completely different directions. For planets, that idea reaches much deeper. A slight difference in distance from the Sunday, a slight difference in the amount of water present at the beginning, a slight difference in the atmosphere, volcanic activity, magnetic field, or the way rock and gas interact. Changes that seem small at first can, when stretched across billions of years, transform two similar worlds into places that barely resemble one another. Earth, the world where we live, is not a perfect planet. It has storms, earthquakes, volcanoes, droughts, ice, deserts, deep oceans, and climatic changes that have reshaped life many times. Yet amid all these disturbances, Earth has maintained a rare kind of balance. Water can remain liquid on the surface, rain can fall, and eventually return to the ocean. Carbon can move through the atmosphere, living organisms, oceans, and rocks in cycles, lasting immense periods of time. The atmosphere is thick enough to preserve warmth, but not so thick that it traps light and heat beyond control. Nights can be cold and days can be hot, but throughout much of its recent history, this planet has still allowed life to take root, change, and continue. Venus is different. It is also a rocky planet, nearly the same size, and located within the inner solar system. But its atmosphere followed a far more extreme path. The air there is nothing like the air we breathe. It is thick, heavy, and composed mainly of carbon dioxide. On Earth, carbon dioxide makes up only a small part of the atmosphere, yet it is still important enough to influence global temperatures. On Venus, it became the dominant atmospheric gas, wrapping the planet in a blanket far too thick and trapping so much heat that the surface remains under constant, intense heating. What is worth considering is that Venus was not necessarily a completely alien planet from the beginning. Its closeness to Earth is precisely what gives the story greater depth. When we look at a world that is entirely different, such as a giant planet made mostly of gas without a clearly defined solid surface, it is easy to accept that it belongs to another kind of existence. Venus is different. It has rock, it has mountains, it has terrain. Its interior has undergone processes associated with rocky planets. From far away, it is the kind of planet that might make us imagine a more familiar surface hidden beneath the clouds. Then science tells us that beneath those clouds is not a green world, but hot, dry ground compressed beneath overwhelming pressure. Perhaps this is why the description, Earth's twin sister, is both accurate and incomplete. It is accurate because the physical bodies of the two planets share many similarities. It is incomplete because their fates are so different that they seem almost opposite. One has blue oceans and clouds of water. The other has clouds of acid and a scorched surface. One has mornings filled with breathable air. The other has a murky yellow light filtered through a dense atmosphere. One allows plants, animals, and human beings to exist. On the other, even machines can survive for only a short time. But it is important not to turn Venus into a simple image of terror. It is not an evil version of Earth in any careless sense. It is a real planet with its own history and its own physical and chemical laws. It did not become hostile because of punishment or mythology. It became this way because its atmosphere, temperature, water, rock, and sunlight interacted along a different path. These processes may unfold so slowly that no living creature could perceive them within a single lifetime. But accumulated across immense spans of time, they are powerful enough to transform the entire face of a world. From here, Venus is no longer a simple answer, but the trace of a very long history. The two planets may once have shared many qualities, yet over billions of years, small differences gradually pulled them in opposite directions. Venus lies closer to the Sun and receives more energy. If liquid water once existed on its surface, it may have evaporated and gradually escaped into space. Its carbon dioxide-rich atmosphere trapped heat too effectively, making it increasingly difficult for the planet to cool. Within Venus, volcanoes, the rocky crust, and the cycles that might regulate climate did not operate in the gentler way they do on Earth. None of this happened in a single moment. It was more like many small doors closing one after another, until Venus crossed a distant threshold from which returning to its earlier balance was no longer easy. When we ask these questions, we are also asking questions about Earth. Studying Venus is not merely the study of another planet. It is like looking into a distant mirror where the reflection is not the same as us, yet remains close enough to demand our attention. In that mirror, we see that an atmosphere is not simply a passive background. It can determine how much heat is retained, whether water can remain, and whether the surface becomes mild or stays under relentless heat. We see that for a planet to support life, it needs more than rock and sunlight. It requires an extremely delicate coordination among distance, water, clouds, gases, temperature, internal activity, and time. There is a special quietness in thinking about these two planets. Earth and Venus both orbit the Sunday. Both were born from the material of a young solar system. Both have spent billions of years beneath the light of the same star. Yet one became a home, and the other became a reminder. One has oceans reflecting white clouds. The other hides its ground beneath brilliant layers of acidic cloud. One has the sound of rain falling on rooftops. On the other, droplets of acid may form high in the atmosphere and evaporate before ever reaching the surface. Both are real planets, but only one allows us to sit quietly at night and listen to a story about the other. Calling Venus Earth's twin sister is therefore not only a way of saying that it resembles us. The name also emphasizes something deeper. Only a few differences, given enough time, can create an enormous distance between a habitable world and one that cannot be reached. Venus is strange not only because it is extreme. It is strange because, judging by its original characteristics, it might not seem so far removed from us. Seen in this way, the brilliant light visible from Earth is no longer only beautiful. It becomes the outermost layer of a much larger secret. Beneath it lies a dense atmosphere. Within that atmosphere is the heat trap that makes Venus even hotter than Mercury. Farther below lies rocky ground, volcanoes, and traces that may tell of a past far more complex than we currently understand. To learn why this twin sister did not share Earth's fate, we must first look into the very thing that creates its outward beauty. Clouds so bright and so thick that they conceal everything beneath them. From a distance, Venus appears almost completely unmarked. Every sign of the harsh surface below is hidden behind the smooth brightness surrounding the planet. Scorching plains, volcanic rock, and ground compressed beneath a crushing atmosphere all remain beyond human sight. What reaches us is only a powerful, steady light, so beautiful that it is easy to mistake it for the beauty of peace. Yet that very impression makes Venus even more mysterious. Its brilliance does not come from a gentle world beneath the clouds, but from the dense cloud layers reflecting sunlight while concealing nearly everything behind them. When seen from space, Earth reveals the blue of its oceans, the white of its water clouds, and the brown and green patterns of its continents. Venus, by contrast, has almost no recognizable face in ordinary visible light. It resembles a glowing sphere, completely covered by continuous layers of cloud. No blue oceans appear. No continents can be distinguished by the human eye. There are none of the familiar, bright and dark regions visible when Mars is observed through a telescope. Venus appears only as a yellow-white globe of light, soft on the outside and sealed within, like a door that has remained closed for a very long time. Those clouds are the reason Venus shines so brightly in Earth's sky. When sunlight reaches the planet, the cloud layers surrounding it reflect a large portion of that light back into space. The more light an object reflects, the brighter it appears to us. On Earth, we can sense something similar on days filled with white clouds, when the sky remains softly illuminated even without intense direct sunlight. Snow does the same, so does pale sand, and so does still water. They do not create their own light. They return the light they receive. Venus does not produce light like a star. It shines because it catches sunlight, and its dense clouds reflect that light back toward us. But the clouds of Venus are not the clouds human beings are accustomed to seeing from the ground. On Earth, the word cloud usually brings to mind water vapor, shade, rain, or the cooler air that follows a hot afternoon. In human memory, clouds are often connected to life. They shelter fields from sunlight, gather water into rain, drift over mountains and hills, and leave behind a sense of softness. The clouds of Venus belong to a very different chemical world. They contain tiny droplets of sulfuric acid suspended within the dense atmosphere. From far away, those droplets help make the planet shine. But seen from close range, they are not a gentle veil. They form a corrosive covering, cold in the upper atmosphere but hiding beneath it a planet so hot that no rain can reach the ground in the familiar way. This gives the beauty of Venus an unusual character. It is not the beauty of transparency, but the beauty of concealment. Venus is not beautiful because we can see so much. It is beautiful because we can see almost nothing below. The clouds make the planet look smooth, bright, and even without complicated features. But that smoothness is like the surface of a sealed box. The brighter it becomes, the more it hides. The more beautiful it appears, the harder it is to understand. Light becomes a kind of silence, and the clouds become the boundary between what human beings imagine and what the planet is truly holding inside. For a long time, these clouds made Venus extraordinarily difficult to understand. Before spacecraft, radar, and direct measurements existed, people imagined many possibilities for what might lie below them. Some once believed that the dense clouds could conceal jungles, swamps, oceans, or a hot and humid world resembling the ancient Earth. Those ideas were not unreasonable within the knowledge of their time. When no one could see through the clouds, imagination naturally filled the empty space with familiar images. A planet almost the same size as Earth and completely covered in cloud could easily suggest water, rain, and a protected surface below. But as science advanced, the clouds began to reveal a different meaning. They were not evidence of a humid paradise, but of an extreme atmosphere, an atmosphere thick enough to enclose the entire planet. A cloud system that never opens into blue skies like those of Earth, and a highly reflective layer that makes Venus shine brilliantly while concealing almost all of its surface. Sometimes the truth about a planet is not found in what we can see, but in the reason we are unable to see anything more. Standing on Earth and looking toward Venus at dusk, we see only a quiet point of light. But as the imagination moves closer, that point gradually becomes a planet wrapped in many layers of cloud. High in the atmosphere, sunlight is scattered, reflected, and softened into pale yellow tones. Currents of gas move around the planet, carrying tiny particles of acid. There is no clear opening through which the human eye could look down at the surface. There is no blue window like the gaps that sometimes open between clouds on Earth. There is only a continuous covering, a sky that does not easily clear, a veil that has existed long enough to turn Venus into a symbol of mysterious beauty. And beneath that veil, heat remains trapped. Some sunlight can enter and warm the planet, but when the heated surface releases energy, the thick atmosphere prevents much of that heat from escaping. The clouds are not the only reason Venus is so extreme, but they are the first visible sign we notice from far away. They tell us that this planet does not function like Earth. It has a different atmosphere, a different way of retaining heat, a different way of reflecting light, and a climate history that has moved far beyond the balance familiar to us. Perhaps this is why Venus feels both near and distant. It is near because we can see it with the naked eye, and because it repeatedly returns to the sky like someone familiar. It is distant because even while looking directly at it, we see only the outermost layer. It is near because it is a neighboring planet. It is distant because its clouds prevent us from understanding it through ordinary intuition. On Earth, clouds change quickly. A morning may begin gray and become sunny by noon. A storm may pass and leave behind a clear sky. On Venus, the covering feels far more permanent and complete, as though the planet has hidden itself inside a garment that cannot easily be removed. These clouds also change the way we think about beauty in the universe. Not everything bright is gentle. Not everything beautiful from far away is easy to touch. A planet that shines in the sky does not necessarily possess a peaceful surface below. Venus reminds us that the universe does not always reveal the truth through its first appearance. Sometimes light is an invitation. Sometimes light is a curtain. And in the case of Venus, its greatest brilliance is also the clearest sign that much remains hidden. Once we understand this, we can look again at the morning star or the evening star with a different feeling. Venus remains beautiful. That beauty does not disappear simply because we know that a harsh world lies beneath it. Instead, it becomes deeper. The light is no longer only a simple point in the sky. It is sunlight reflected from clouds of sulfuric acid. It is the visible face of an atmosphere that is dense and unfamiliar. It is the outer appearance of a planet that humanity required a very long time to begin understanding. It reminds us that some secrets are not hidden in darkness, but within brightness itself. The journey into Venus now becomes slower and deeper. We cannot look only at the surface appearance and reach a conclusion. We must learn to ask why the planet shines, why it remains hidden, why its light does not reveal an easily visible surface, and why a world so similar in size to Earth is wrapped in such different clouds. Once this first veil has come into view, what waits below is no longer the gentle brightness of the morning star or evening star, but the weight of an atmosphere so dense that even light seems to grow tired while passing through it. As we move downward from the bright clouds that make Venus shine so brilliantly in our sky, our sense of the planet begins to change. The light no longer feels as gentle as it does when seen from Earth. It is filtered through layer after layer of gas, dimmed and stained into a murky yellow that is difficult to name. Beneath the clouds, space does not open into a clear blue sky, nor does it carry the fresh, open feeling of air after rain. Everything seems denser, as though light itself, upon entering Venus, must pass through an atmosphere too thick to preserve its original clarity. On Earth, we are so accustomed to living inside an atmosphere that we rarely think about it. The air around us is transparent and light. It can move as wind and carry the scent of damp soil, leaves, the ocean, or a city in the morning. We breathe it, walk through it, and hear sound travel within it. Because it is so familiar, we easily forget that an atmosphere has weight. An enormous layer of air rests above our heads, but our bodies have adapted to that pressure since birth, so we do not feel ourselves being crushed beneath it. It is like a background condition of life, always present but rarely noticed. Venus also has an atmosphere, but it is not a gentle layer of air like Earth's. It is made mostly of carbon dioxide, a gas that forms only a small part of Earth's atmosphere, but still plays an important role in retaining heat. On Venus, carbon dioxide is no longer a minor component. It has become almost an entire ocean of gas surrounding the planet, so dense and heavy that the surface below is pressed beneath an enormous weight. If we imagine an atmosphere as a blanket, Earth's blanket is just thick enough to keep a habitable world warm. Venus's blanket is so thick that protection has become imprisonment. A descent through the atmosphere of Venus would be nothing like passing through clouds on Earth. The lower one travels, the denser the air becomes. The light does not disappear immediately, but it gradually loses its clarity. Colors become heavy, yellowish, and orange, as though everything were being viewed through a hot, clouded pane of glass. The temperature rises, the pressure rises as well. Space no longer feels open, but instead seems to close in from every direction. A spacecraft falling through this atmosphere is not simply moving from a higher altitude to a lower one. It is traveling from a brilliant outer covering into a world where the gas itself has become a very real physical force. Pressure may sound like a dry scientific concept, but it can be understood through familiar images. When we dive underwater, the deeper we go, the more our bodies feel compressed. Our ears begin to ache. Our chests feel heavier. The water does not press from only one direction, but from every side. This happens because the mass of water above us creates pressure below. On Venus, the pressure does not come from an ocean of liquid water, but from the atmosphere. Because that atmosphere is so dense and heavy, the pressure at the surface is about 93 times greater than atmospheric pressure at sea level on Earth. In more familiar terms, it is similar to the pressure found nearly 1 kilometer beneath Earth's oceans. That number is not meant only to impress us. It helps us understand that the surface of Venus is not merely a place that is somewhat hotter than Earth. It is an environment in which everything remains beneath the continuous weight of the entire atmosphere. An object resting on the surface must endure more than heat. It is surrounded by compressed gas pressing against it from every direction, as though submerged in a sea of dense, scorching air. Any machine designed to operate there must resist pressure from all sides. Ordinary materials, joints, wires, protective shells, and sensors must all survive a world that offers them no gentleness at all. What is remarkable is that this atmosphere is not merely a thin outer shell surrounding the planet. It is one of the most important forces shaping the fate of Venus. It determines how light travels downward, how heat is retained, and how much pressure the surface must bear. On Earth, when we look upward, the atmosphere often feels light. It is blue during the day, dark at night, and filled with stars when the clouds are gone. On Venus, the sky, if it could be seen from below, would not open into that familiar blue expanse. The dense gas and clouds above make the light murky and diffuse. The sun would not appear as a sharp, clearly defined disk. It would seem more like a hidden source of brightness, scattered through layer after layer of cloud and gas, until only a heavy, yellow, hot, and unfamiliar glow remained. If it were somehow possible to stand on the surface of Venus inside an unimaginable suit strong enough to withstand the heat and pressure, it would not feel as though we were beneath a sky like Earth's. The air would not invite a breath. It would carry no scent of grass, no cool moisture, and none of the pleasant change between morning and evening. It would feel more like an enormous mass of gas that had covered the planet for so long that it compressed everything beneath it, held everything in place, and denied the surface any chance to escape its hot and heavy condition. This would not be air in the familiar sense of life, but an environment closing in from every side. For this reason, when we say that Venus has a thick atmosphere, we are not speaking only about thickness as a number. We are speaking about the weight of a climate history that followed a very different path. A thick atmosphere can protect a planet from smaller changes. It can retain heat and, under certain conditions, make the surface more stable. But when it becomes too rich in carbon dioxide, too heavy, and too enclosed, that stability becomes a trap. The same qualities that might help a planet maintain moderate warmth have, on Venus, helped transform warmth into heat, with no easy way to escape. There is a striking contrast between the planet's outer appearance and what lies within. From Earth, its reflective clouds make Venus look like a peaceful point of light. But once we pass through that brightness, we encounter an atmosphere that is anything but light. The radiance outside does not lead into a bright and comfortable place. It leads downward into an environment compressed by carbon dioxide, stained yellow by clouds and gas, and burdened by pressure far beyond anything the human body experiences on the surface of Earth. This also helps explain why spacecraft sent to Venus have always faced challenges very different from those encountered on many other worlds. They must do more than cross the distance through space. They must do more than enter the correct trajectory or land safely. They must enter an atmosphere where every meter downward brings them closer to greater heat, pressure, and corrosion. Before ever reaching the ground, they must survive a journey through thick clouds and dense gas, where even continuing to transmit a signal, collect measurements, or remain functional for a few more minutes is already an achievement. Seen this way, the atmosphere of Venus is no longer a background element in the story. It is one of the main characters. It makes the planet shine in our sky. It hides the surface from ordinary telescopes. It presses down upon the ground, and it prepares the way for an even deeper mechanism, the trapping of heat. Pressure makes Venus harsh, but pressure is only part of the secret. What truly transforms this planet into a world of almost unimaginable heat is the way its dense atmosphere captures warmth, holds it, and allows almost none of it to escape. As we leave the clouds behind and descend deeper into the atmosphere, we begin to understand that Venus is not merely covered. It is trapped inside its own air, a yellow, carbon dioxide-rich atmosphere, heavy as the deep sea and growing hotter closer to the ground. That weight alone is enough to make the surface hostile, but what lies behind it is even more important. A dense atmosphere does more than press downward. It can wrap itself around heat, hold onto every portion of energy the planet tries to release, and gradually turn the entire world into an enormous room with no door through which the warmth can escape. The atmosphere of Venus is not only heavy. If weight were its only defining feature, the story of this planet would be much simpler. The enormous pressure at the surface presses inward from every direction. But what makes Venus one of the harshest places in the solar system lies in a quieter ability, its ability to retain heat. The thick atmosphere surrounding the planet is not only like an ocean of gas pressing down on the ground. It is also like a blanket that has become far too thick, covering the world so completely that the heat below can barely find a way to escape. To understand this, it may help to begin with Earth itself. Every day, sunlight passes through the atmosphere and reaches the ground, the oceans, trees, rooftops, and streets, warming everything it touches. When night arrives, Earth's surface releases some of that heat back towards space, but not all of it escapes. Part of the warmth is held within the atmosphere by gases such as water vapor, carbon dioxide, and several others. This mechanism is commonly called the greenhouse effect. The name may sound technical, but the idea is familiar. The atmosphere acts like a covering that prevents a planet from cooling too quickly. The natural greenhouse effect is not a bad thing. In fact, Without some warmth being retained, Earth's nights would be far colder, and the planet's average temperature could fall so low that life as we know it would struggle to exist. Because the atmosphere holds heat at a moderate level, Earth can have oceans that do not freeze completely, rivers that continue to flow, rain that returns to the ground, and mornings that do not feel completely hostile to living bodies. The problem begins only when a necessary mechanism becomes too strong, like a good blanket on a cold night that becomes suffocating when too many layers are added. On Venus, that blanket is thicker than anything familiar to us. Its atmosphere is composed mainly of carbon dioxide, and the amount is not merely somewhat greater than on Earth. It is dense enough to surround the entire planet within an enormous heat trap. Some sunlight can still enter, passing through the clouds and atmosphere to warm the surface. But when the ground tries to release that energy again, the thick carbon dioxide absorbs and retains much of the heat. It cannot escape easily. It remains trapped, is redirected downward, accumulates, and keeps the surface intensely hot in a condition that is almost completely sealed. We can imagine Venus as a room with every door tightly closed. During the day, sunlight still passes through the windows, warming the floor, the walls, and the objects inside. But when those surfaces begin releasing heat, the doors do not open to let the warm air escape. The heat continues circulating within the room, layer upon layer. At first, the room is only warm, then it becomes hot. If this continues for long enough, the rising temperature is no longer a small change. It becomes the new condition of the entire room. Venus is similar, except the room is the size of a planet, and its thick atmosphere has nearly sealed every path through which heat might escape. This is why Venus is hotter than Mercury, even though Mercury is closer to the Sunday. At first, this seems to go against intuition. We naturally assume that the closer a world is to the Sun, the hotter it must be. And in many situations that is true. Mercury receives far more intense sunlight than Venus, but it has almost no thick atmosphere to hold the heat. Daytime temperatures on Mercury can become extremely high, but when a region rotates into darkness, heat can escape into space more quickly. Venus is different. It receives less sunlight than Mercury, yet it is extraordinarily effective at trapping heat. Its carbon dioxide-rich atmosphere has made Venus the planet with the hottest surface in the solar system. The average surface temperature of Venus is about 467 degrees Celsius. That number is difficult to grasp when heard only once. It is far hotter than an oven in a human kitchen. It is high enough that many familiar materials could not endure for long. Rock, metal, machinery, sensors, anything sent there must face a level of heat that does not ease during the night as it does on Earth. Because the atmosphere is so thick and retains heat so efficiently, the difference between day and night at the surface is not like a place that becomes hot under daylight and cooler after dark. Heat surrounds almost the entire planet, persistent and heavy, like a summer with no cool evening and no night in which to recover. The most unsettling part of this heat trap is not that it appeared suddenly like an explosion. Venus did not become this way in a single moment. A runaway greenhouse effect is a process pushed beyond a threshold of balance, slower, deeper, and far more difficult to reverse. As a planet warms, any surface water it possesses evaporates more easily. Water vapor is itself a powerful greenhouse gas. The more water vapor enters the atmosphere, the more heat is retained. That additional heat makes it even harder for liquid water to remain stable on the surface. A feedback loop begins. Warming causes water to evaporate. Water vapor traps more heat, and the temperature rises further. On Earth, water is not only a liquid stored in rivers and oceans. It also participates in the mechanisms that help regulate the planet. Water evaporates, forms clouds, falls as rain, enters soil and rock, and returns to the sea. Together with the rocks and the atmosphere, water takes part in long cycles that help prevent the climate from drifting too far away from habitable conditions. But if a planet gradually loses its water, those regulating mechanisms weaken as well. There are no longer oceans to absorb heat. There is no rain to carry part of the carbon into rocks through slow natural processes. The gentle system that once allowed the surface and atmosphere to exchange material in a less extreme way begins to disappear. Venus today has almost no liquid water on its surface. This makes the question of its past extremely important. If it once had water, even during a distant period of its history, the loss of that water may have played a major role in the path that led to its present state. When water vapor rises high into the atmosphere, sunlight can break the water molecules apart. Hydrogen, the lightest component, can escape into space more easily. Over immense periods of time, little by little, the planet may lose the very material that once helped it regulate itself. What remains is an atmosphere rich in carbon dioxide, clouds of acid, extreme heat, and a surface without oceans to help maintain balance. But this should be understood calmly. Venus is not a simple image of what Earth will become in the near future. Earth cannot transform into Venus in a single day or even within one short century in the exact same way. The two planets have different histories, different distances from the Sun, different amounts of water, and different geological and atmospheric systems. What Venus shows us is not an easy threat, but a deeper principle. An atmosphere can help determine the fate of a planet. When the composition of the atmosphere changes, the way heat enters and leaves changes as well. When a system is pushed too far from balance, a world can cross into a state that is extremely difficult to reverse. The carbon dioxide heat trap is therefore not just one scientific detail among many. It lies at the center of Venus's secret. The clouds make the planet shine. The dense atmosphere creates overwhelming pressure at the surface. But it is the atmosphere's ability to retain heat that transforms sunlight into imprisoned warmth. Energy entering the planet does not always return easily to space as heat. Part of it remains trapped. Part of it is redirected toward the surface. Part of it continues adding to the planet's temperature. Over long spans of time, Venus has not simply received heat. It has become trapped within it. There is a heavy silence in that image. No enormous flames cover the surface. No global ocean of lava spreads across the entire planet, as extreme imagination might suggest. There is only a dense atmosphere, hot ground, reflective clouds, and a physical process that is quiet but persistent. That quietness is part of what makes Venus so thought-provoking. It reminds us that the greatest changes do not always arrive as sudden disasters. Sometimes they come through mechanisms that are steady, slow, and almost impossible to notice in any single moment, yet continue accumulating without pause across time. If we return to the image of Venus as a bright point in the sky, that light now carries another layer of meaning. From Earth, Venus remains beautiful. It can still rest quietly at the edge of twilight, announce the approach of dawn, and give the viewer a sense of calm. But inside that brightness lies a world where heat is not released, where carbon dioxide has become a climatic lock, and where the surface remains at such a high temperature that there is almost no relief. The beauty seen from far away is still real. We simply understand now that it is created by a system that is not gentle. Venus is no longer merely a hot planet. It becomes a lesson in what can happen when an atmosphere becomes too efficient at retaining heat. Pressure makes the planet heavy and oppressive, but heat is what turns it into a place where familiar forms of life cannot survive. And once we understand that heat trap, we can continue descending toward the surface, where everything stops being an abstract idea and becomes hot rock, murky yellow light, silent machinery, and a world so extreme that even metal can no longer preserve the strength we normally expect from it. Once the heat trap of Venus becomes clearer, the surface beneath that atmosphere no longer feels like an abstract place. It begins to emerge as real terrain, with rocks, light, and a horizon, yet everything exists under conditions so extreme that they are difficult to imagine through any experience on Earth. The heat there does not arrive like a summer afternoon and then soften as evening approaches. It is not warmth rising from a road after a few hours of intense sunlight. It is an almost permanent temperature surrounding the entire planet, quiet but persistent, as though Venus had been placed inside an enormous furnace that never truly turns off. If we could look down upon that surface, the first thing we saw might not be a landscape filled with flames. Venus does not need fire to appear frightening. The light there may be dim and murky yellow, filtered through the dense atmosphere and the clouds above. Even the sun, if visible at all, would no longer appear as the clear disk we know in Earth's sky. It would resemble a distant source of light hidden behind many layers of gas, leaving behind a heavy kind of daylight with little clarity and no sense of open space. The rocks beneath that light do not cool. There are no trees casting shade across the ground. There are no oceans to absorb part of the heat, and no rivers carrying cooler water through valleys. Nearly the entire planet is immersed in a dense, compressed, and remarkably uniform heat. The surface temperature of Venus is about 467 degrees Celsius. That number is so high that many familiar comparisons from Earth begin to lose their meaning. An oven in a human kitchen is hot enough to cook food within a short time, yet the surface of Venus is far hotter than anything required in ordinary life. Some familiar metals would begin to soften. Some instruments would lose their ability to function. Connections and electronic components could quickly fail beneath the combined effects of heat, pressure, and a hostile chemical environment. It is a place where not only living bodies cannot survive, but even machines built by human beings must struggle from one minute to the next against a world that does not tolerate fragility. What makes the heat on Venus different from that of many other places is that it does not belong only to the daytime. On Earth, even when a desert becomes intensely hot beneath the high sun, night usually brings some relief. Heat escapes, the air changes, and the ground gradually cools. Venus does not easily receive such a pause. Its atmosphere is so thick and so effective at holding heat that the division between day and night at the surface does not produce the kind of sharp contrast we know. The warmth is retained, distributed, and spread across the planet. Whether the region above is facing light or darkness, the ground remains in an almost continuous state of intense heating. A place like this contains none of the familiar signs of comfort found on a habitable world. There is no surface water reflecting the sky. There is no damp soil after rain. No roots hold onto the rocks, no moss grows within cracks, and no cool wind passes across fields. The surface of Venus is known through rare images and data returned by spacecraft. Rocks, uneven ground, and a gray-yellow world beneath heavy light. The ordinary appearance of stone within such an extraordinary environment makes the scene feel even stranger. It is not a colorful science fiction dream. It looks like real land, but land placed under conditions completely unfamiliar to every living sense we possess. In the history of space exploration, there is something that invites a moment of quiet reflection. Human beings have sent machines down there, not merely past the planet, and not only into orbit, but through the clouds, into the dense atmosphere, onto the surface of Venus, where they transmitted data back to Earth. Several of the Soviet Venera spacecraft accomplished this. They were designed to withstand enormous pressure, extreme heat, and a hostile environment, like small metal boxes carrying human eyes into a place where no human being could go. Imagine a machine descending through the brilliant clouds that make Venus appear so beautiful from far away. At first, it is only a faint signal in space. Then the planet gradually pulls it into the dense atmosphere. Pressure rises around it. The temperature becomes increasingly severe. The light outside changes color and loses its clarity. Instruments within the spacecraft struggle to remain stable. Sensors continue collecting data. During the brief time they are permitted to survive, cameras turn toward the ground. Finally, after a descent in which every atmospheric layer presents another challenge, the machine touches the scorching surface of Venus. That moment is not loud in the way films often imagine. No cheers echo across the planet. No witness stands nearby. and no flag is raised above the ground. There is only a small machine within a hot and heavy world, sending weak but precious signals toward Earth. Images of the surface begin to appear. Scattered rocks, uneven ground, and gray-yellow light covering everything. To us, they are only a few photographs and sets of measurements. To science, they are evidence that what lay beneath the clouds was no longer merely a matter of imagination. The surface of Venus had truly been seen, even if only for a very short time. The longest surviving spacecraft on the surface of Venus lasted only a little more than 2 hours. In ordinary life, 2 hours may feel like a considerable amount of time. In the exploration of another planet, it is only a fragile moment. A machine travels tens of millions of kilometers, survives its trajectory, atmospheric entry, overwhelming pressure, and landing, and then has only a brief period in which to work before falling silent forever. Yet that brief survival makes the achievement even more worthy of respect. Every minute that the signal continued was another minute in which humanity could hear the distant voice of a world hidden from view. Every photograph returned was a small fragment recovered from a place that seemed almost unwilling to be seen. The silence afterward carries a meaning of its own. When the spacecraft stops functioning, Venus does not change. The atmosphere continues pressing downward. The heat remains. The clouds keep reflecting sunlight back into space, allowing the planet to continue looking beautiful and peaceful from Earth. The machine remains on the scorching ground, gradually damaged by heat and pressure, while its final signal has already passed upward through the atmosphere, crossed the emptiness of space, and reached human beings as a very brief greeting from a very distant place. Those few images make Venus feel more real. Before them, we could speak of temperature, pressure, carbon dioxide, acidic clouds, and the greenhouse effect. But once we see rocks on the surface, all those ideas suddenly have somewhere to rest. The heat is no longer only a number. It lies across every slab of stone. Pressure is no longer merely a comparison with the depths of an ocean. It surrounds the lander from every direction. The clouds are no longer only the reason Venus appears bright. They form a sealed roof above ground that is quietly being baked below. The more we understand that surface, the more layered the distant beauty of Venus becomes. The bright point in the sky does not lose its gentleness, but that gentleness is now joined by another kind of understanding. Beneath the light are clouds. Beneath the clouds is a dense atmosphere. Beneath that atmosphere is a temperature capable of exhausting machinery. And upon that ground, small human-made machines once remained for a few dozen minutes or a few hours, looking around through electronic eyes before becoming silent. Those rare images show that beneath the brilliance is not a dreamlike world, but ground heated in silence. Yet Venus is strange in another way as well. While its surface remains trapped beneath almost unchanging heat and pressure, the rhythm of time across the entire planet moves with astonishing slowness. A day there does not pass like a day on Earth. And when Venus is viewed from orbit, we encounter another paradox, a hot and heavy world sealed within a dense atmosphere, yet rotating on its axis more slowly than it completes its journey around the Sunday. On the surface of Venus, everything seems to be held in the same condition for an extraordinarily long time. Rocks rest beneath murky yellow light. The heavy atmosphere presses down against the ground. The heat offers no clear pause like an evening on Earth. If we looked only from below, we might feel that time itself had been compressed there, moving as slowly and densely as the planet's atmosphere. But to understand the rhythm of time on Venus, we need to leave that scorching ground for a moment, rise above the dense atmosphere, and look at the entire planet from the outside. From orbit, Venus is strange not only because of its heat, acidic clouds, and immense pressure. It is also strange because of the way it rotates. Earth gives us a deeply familiar sense of time. A day is the period during which the sun rises, moves across the sky, sets, and then returns the following morning. A year is the much longer journey completed when our planet travels once around the Sunday, Because we have lived within this rhythm since birth, it feels so natural that we hardly need to think about it. Days are short, years are long, morning and evening follow one another steadily. The seasons arrive and depart within a larger cycle. Venus makes all of this different. The planet completes one orbit around the Sun in about 225 Earth days. That is one Venusian year, if a year is understood as the time a planet takes to complete one journey around its star. But Venus requires about 243 Earth days to rotate once around its own axis. This means that, by the measure of axial rotation, one day on Venus lasts longer than one of its own years. While Earth completes a rotation roughly every 24 hours, Venus turns so slowly that before it can finish rotating once, it has already completed an entire journey around the Sunday. At first, this may seem to go against intuition, but it becomes clearer when we separate the two motions. A planet can always do two things at the same time: rotate around its own axis and travel around the Sunday. On Earth, these rhythms are very different. The rotation is fast, while the orbit around the Sun takes much longer. On Venus, however, the rotation is unusually slow. The planet is like someone who walks all the way around a large field before managing to complete one full turn in place. Its movement around the Sun is faster than its rotation around itself. If it were possible to stand safely on Venus, this would make the experience of day and night profoundly unfamiliar. Of course, no human body could truly stand there. The surface is far too hot, the pressure is overwhelming, and the atmosphere cannot be breathed. But even through scientific imagination, we can understand that the sky would resemble no morning on Earth. The sun would not rise quickly, travel across the sky, and set within a familiar span of time. If it could be seen through the thick clouds, its motion would be far slower, as though the entire planet were stretching the interval between light and darkness beyond anything suited to the human sense of time. Even the image of watching the sun rise on Venus is only a convenient way to explain the idea. The clouds are so thick that the surface has no clear blue sky through which a sharply defined sun could be seen. By the time sunlight reaches the ground, it has been filtered, scattered, and dimmed through many layers of gas and cloud. A Venusian dawn, if it can be called that, would not resemble a red-orange disk rising above the horizon. It might feel more like an extremely gradual change in the murky yellow brightness of the surrounding world, a day arriving without a clear edge, without an open sky, without birdsong, and without the cool wind of early morning. This slow rotation comes with another unusual feature. Venus turns in the opposite direction from most planets in the solar system. Earth, Mars, and many other planets rotate in the direction we think of as familiar. Venus rotates the other way. Scientists call this retrograde rotation, but it can be understood simply as a planet spinning in the direction opposite to most of its neighbors. On Earth, the sun rises in the east and sets in the west. On Venus, because of its reversed rotation, the directions of sunrise and sunset would be reversed. This alone makes Venus seem like a world moving outside the usual habits of the solar system. Not outside them in the sense of being wrong, because planets are under no obligation to behave in ways that feel familiar to human beings. But the difference reminds us that every world has its own history. Whether a planet rotates quickly or slowly, tilts strongly or only slightly, and turns in the same direction as its neighbors or the opposite direction may all be connected to ancient collisions, gravitational forces, tides raised by the sun, and changes unfolding across billions of years. The precise origin of Venus's unusual rotation remains part of a more complicated story. It may have been influenced by gravitational interactions acting over immense spans of time. Its dense atmosphere may also contribute to the way the planet exchanges force and energy with the Sun. But at the simplest level, the important point is that Venus differs from Earth not only in temperature. It also measures time according to another rhythm. The idea of a day longer than a year almost feels dreamlike. On Earth, a year contains a great many days, It is long enough for spring to pass, summer to grow warm, autumn to soften, and winter to return. Within a single year, human lives may change. Trees may grow leaves and later lose them. Children may become a little older, and cities may pass through countless mornings and late nights. On Venus, however, one rotation around the axis lasts longer than an entire journey around the Sunday. Time there does not carry the quick breathing rhythm of dawn and dusk. It stretches outward slowly and strangely, almost as though it were not designed for any creature that depends on regular cycles as we do. This slowness also helps us understand why earthly intuition cannot be used to picture every other planet. We carry many deeply rooted assumptions. Skies are blue, clouds bring rain, nights are cooler, and days are shorter than years. Venus loosens each of those familiar ideas, one by one. Its clouds are not gentle clouds of water. Its light does not reveal a clear sky. Its atmosphere is not light enough to breathe. Its surface does not cool like land after sunset. And time itself does not move according to the rhythm the human body knows. Perhaps a machine left behind on the surface of Venus, after its signal ended, would not experience the changing of day and night in the way an object on Earth does. It would remain within the heat and pressure, beneath dim light and a heavy atmosphere, while the planet below turned so slowly that one rotation lasted longer than its journey around the Sunday. Everything there makes motion difficult to grasp. The surface seems almost motionless beneath its crushing heat. The planet's axis turns slowly. Its orbit around the sun continues. And above it all, thick atmospheric layers cover the entire world. What is fascinating is that Venus is not completely calm simply because it rotates slowly. The rocky body itself turns at an almost motionless pace, but the atmosphere above does not share that rhythm. This is one of the planet's most beautiful and difficult paradoxes. Below, the ground rotates like the hand of a clock that barely seems to move. Above, the cloud layers can travel rapidly around the planet, far faster than the surface beneath them. It is as though Venus contains two different rhythms at once: the deep, slow rhythm of the rocky world and the fast, flowing rhythm of the atmosphere. From far away, the bright point of Venus reveals none of this. It does not tell us that a year there is shorter than one axial rotation. It does not show that the planet spins in the opposite direction from most of its neighbors. Nor does it reveal the contrast between the slowly turning surface and the rapidly moving clouds above. But the deeper we travel into the story, the more its outward beauty becomes a doorway leading towards stranger laws. Venus is not merely a hot place. It is a planet with a different kind of time, different light, a different atmosphere, and patterns of motion that force us to relearn the meaning of a day, a year, a morning, and an evening. Once that slow rotation comes into view, another secret begins to open above the clouds. Even more unusual is the fact that while the planet itself turns with extraordinary slowness, its atmosphere moves at an entirely different speed. The cloud layers that make Venus shine so brightly in our sky do not remain still like a curtain wrapped around the planet. They race around the world high above the surface, carried within an enormous atmospheric system that human beings are still trying to understand. Venus rotates so slowly that time on the planet seems to have been stretched. One complete turn around its axis takes longer than its journey around the Sunday. Thinking only about that, it is easy to imagine Venus as an almost motionless world, a hot sphere of rock turning slowly through space, completely covered by clouds and trapped within its own heat. But that image is accurate only for the deeper layers below. The higher we rise, and the closer we come to the clouds that make Venus shine so brightly in Earth's sky, the more we enter an entirely different rhythm of motion. At those heights, the slowness of the rocky planet no longer seems to control the story. The upper atmosphere moves far more quickly, almost as though it possesses a life and rhythm of its own. The clouds do not simply remain wrapped around Venus like a still layer of fabric. They drift, twist, stretch, change shape, and continue racing around the planet within a vast circulation. while the surface below requires about 243 Earth days to complete one rotation. The upper atmosphere can travel around Venus in only about 4 days. This enormous difference creates one of the planet's most fascinating and difficult mysteries. Venus itself rotates with extraordinary slowness, while its sky moves remarkably fast. Scientists call this phenomenon atmospheric superrotation. The term may sound complicated, but the basic idea is simple. It occurs when an atmosphere circles a planet much faster than the surface beneath it rotates. Imagine a sphere turning so slowly that its motion is almost impossible to notice, while the air surrounding it slides rapidly around and around. The atmosphere does not leave the planet, but neither does it move in step with the ground. It is like an enormous river made of clouds and gas, flowing around a hot and heavy world, constantly carrying energy from one region to another. On Earth, winds can also become frighteningly powerful. Storms sweep across oceans, high-altitude air currents carry clouds across great distances, and differences in pressure create complex weather. But Earth's atmosphere remains connected to the rotation of the planet in a more familiar way. Oceans, continents, mountains, forests, ice, water vapor, and the changing cycle of day and night all help shape the weather. The air moves, but it belongs to a world with a varied surface, with water that moderates temperature, with seasons, and with many different climate zones. Venus has none of those gentler conditions. Beneath its clouds lies a dry and scorching surface, with no oceans to absorb and redistribute heat, no forests exchanging moisture with the atmosphere, and no rain reaching the ground to cool the rocks. Its atmosphere is extraordinarily dense, heat remains trapped for immense periods, and sunlight interacts with the cloud layers in ways very different from what happens on Earth. From all these conditions, an enormous atmospheric machine emerges. It does not operate through the peaceful motions we often associate with clouds, but through broad and powerful currents that sweep around the planet at speeds that can reach approximately 360 kilometers per hour within the cloud layers. A speed of 360 kilometers per hour may bring to mind a race car or an extremely fast train. But on Venus, this is not an object rushing across the ground. It is the air. It is the clouds. It is enormous masses of gas moving within an atmosphere filled with sulfuric acid, carbon dioxide, and heat. They do not travel along a few roads, pass through a city, or cross a mountain range before coming to a stop. They circle the entire planet, surrounding a world already locked inside its heat, continuing to flow high above a surface that rotates too slowly for human intuition to grasp. Part of what makes this phenomenon so difficult to understand is that no single cause can explain everything. Energy from the sun enters the atmosphere. Differences between illuminated and dark regions create contrasts. Pressure changes with altitude. Atmospheric waves travel through the dense gas. Friction, vertical motion, cloud structure, and the way heat is transported all contribute to the larger picture. Each factor is like a small stream joining a much larger river. Together, they produce the rapid movement of the clouds, but exactly how the entire system maintains this rhythm remains a question science has not completely resolved. That unfinished understanding is part of what makes Venus so compelling. It is not a planet that has been fully explained simply because we know it is hot and has a dense atmosphere. Behind every answer lies another layer of questions. How can the clouds move so quickly above a planet that turns so slowly? How is energy transported through the atmosphere? How do those air currents change over time? The answers do not lie within one simple image, but within many measurements, observations, and models connected together. Venus is therefore like an enormous natural laboratory, where an atmosphere operates under conditions unlike anything familiar on Earth. From the surface, if an instrument were strong enough to survive for a long time, it might experience a world almost compressed within heat. But higher above, within the clouds, the planet is not still at all. Cloud patterns change shape. Layers of gas slide past one another. Energy is carried through broad circulations. The air brings no cooling relief, but it still moves. The clouds do not carry rain to the ground, but they continue to drift. The entire atmosphere resembles a vast body operating in silence, producing no sound that human beings can hear from Earth, yet leaving visible traces in every image returned by spacecraft and telescopes. What is especially interesting is that all this motion disappears when Venus is observed with the naked eye. From Earth, the planet becomes only a steady point of light. It does not tremble, visibly change shape, or reveal the cloud currents racing around it. To human eyes, its beauty appears completely still. But that stillness is only a limitation created by distance. As science moves closer, the peaceful point of light opens into a complex atmospheric system, where everything moves far more rapidly than its outward appearance suggests. Venus can be understood as a world with two rhythms existing at once. The first is extremely slow and belongs to the rocky planet itself, to an axial rotation that lasts longer than its orbital year. The second exists within the clouds, fast, powerful, and continuously flowing around the heated world below. These two rhythms are not completely separate, but neither are they the same. Together, they make Venus a planet of contrasts, bright from far away but difficult to understand up close, slowly rotating while its clouds race around it, beautiful in the sky yet severe beneath that brilliance. This contrast also reminds us that an atmosphere is never merely a motionless covering. On any planet with an atmosphere, the air can carry energy, transport heat, form currents, and change the way the world appears from outside. On Earth, we see this in clouds moving across the ocean, in the wind before rain, in summer storms, and in skies changing color during the afternoon. On Venus, the same basic idea is pushed into a much more unfamiliar form. Clouds of acid circling the planet, high-altitude winds moving at tremendous speed, and a surface below that remains trapped beneath heat and pressure. Once we understand this, the clouds of Venus are no longer only a veil hiding the surface. They become an active part of the planet. They reflect sunlight and make Venus shine. They prevent human eyes from seeing the ground. They participate in vast atmospheric circulation. They contain tiny droplets of acid, powerful currents of gas, and chemical mysteries that remain unresolved. From their smooth outward appearance, the clouds gradually reveal themselves as an ocean of gas, high above the surface, a place without blue water or ocean waves, yet with currents, circulation, and power of its own. Clouds usually make human beings think of rain, but rain on Venus is unlike anything beneath Earth's sky. Droplets of acid may form high in the atmosphere and begin falling through air that grows hotter as they descend, only to evaporate before reaching the ground. From far away, these clouds make Venus shine brilliantly. Seen more closely, they are no longer a beautiful curtain, but an enormous river of gas, flowing around a world locked inside its own heat. A place where even rain cannot complete its journey. In the familiar memory of Earth, clouds can drift above rooftops on a quiet afternoon, gather moisture from the oceans, cool the pavement after a hot day, and then return to the ground as rain. They do not simply decorate the sky. They belong to a cycle that nourishes rivers, plants, and soil. Because of this, when we see Venus from far away and learn that the planet is completely covered in clouds, it is easy to bring that same gentle feeling with us. But the closer we move, the more that familiarity begins to disappear. The clouds of Venus do not lead us toward cool water or quiet rain. They open into an entirely different chemical sky. The cloud layers of Venus are not gentle clouds of water like those on Earth. They form several thick layers within the atmosphere, mainly between about 45 and 70 kilometers above the surface. From far away, these clouds reflect sunlight and make Venus one of the brightest objects in our sky. But from closer range, that brilliance is no longer simply the light of white clouds. Suspended within those layers are tiny droplets of sulfuric acid, drifting through the dense atmosphere and being carried by fast winds around the planet. Sulfuric acid is highly corrosive. On Earth, even the name brings to mind laboratories, safety warnings, and substances that should never be touched with bare hands. On Venus, however, it is a natural part of the sky. This is not because the planet is mysterious in a mythical sense, but because its chemistry takes place in an environment very different from our own. Sulfur dioxide, a very small amount of water in the atmosphere, and sunlight can take part in reactions high above the surface. Through these reactions, new compounds form and eventually create tiny droplets of acid within the clouds. This explanation may sound dry when expressed only through chemical formulas, but it can be imagined more gently. High above Venus, where sunlight still acts strongly upon the atmosphere, molecules are broken apart, recombined, and transformed into new chemical forms. The air is not motionless. The clouds are not simply condensed water vapor. They form a vast region of chemical activity, where light, gas, and the last small traces of water come together to create an acidic sky. Within those clouds, tiny droplets can form like rain, but their story is unlike any rainfall beneath the skies of Earth. On Earth, when clouds become heavy enough, water droplets fall. They may land on rooftops, lakes, fields, or roads after a dusty day. The sound of rain is deeply familiar to human beings. Drops tapping against a metal roof, the steady whisper outside a window, water falling from the edge of a leaf. Rain creates contact between the sky and the ground. It is the atmosphere returning water to the planet. On Venus, however, any droplets of acid that begin falling from the upper cloud layers enter an unfinished journey. The farther they descend, the hotter the surrounding atmosphere becomes. Before they can reach the ground, they evaporate again. Venus therefore has a very unusual kind of rain. Rain forms, rain falls, and then rain disappears into the hot air. No droplets of acid strike the rocks, no small streams move across the surface. There are no puddles, no damp marks, and no moment when the ground is cooled. The droplets never complete their journey from cloud to land. They return to vapor, rejoin the atmosphere, and continue within a more enclosed and unfamiliar chemical cycle. A rain begins in the yellow clouds, but the farther it falls, the more it dissolves into the air, as though the atmosphere of Venus refuses to let the sky touch the ground in any gentle way. This image reveals how deeply different Venus is. It has clouds, but those clouds bring no comforting shade. It has falling droplets, but they never reach the surface. It has a kind of cycle, but that cycle does not nourish oceans, rivers, or forests. On Earth, rain is part of life. On Venus, acid rain is only one brief stage in atmospheric chemistry, a movement that leaves no familiar sound upon the heated rocks below. This also helps us understand why Venus cannot be viewed through comparisons that remain too close to Earth. The same word, cloud, can lead to two very different realities. On one world, clouds mean water vapor, rain, shade, and the cycles of life. On the other, they mean sulfuric acid, reflected sunlight, a hidden surface, and reactions taking place under the energy of the sunday. Even the idea of rain separates into two paths. One reaches the ground and cools the world. The other disappears into the hot atmosphere before leaving any gentle trace. If we imagine Venus as a planetary body, the acidic clouds are like a bright but unhealthy skin. They surround the planet, but they do not heal it. They cover it, but they do not support life. They make Venus shine while keeping the surface hidden. From the outside, these clouds are the reason the planet looks beautiful. From within, they are evidence of an atmosphere that has moved far beyond what human beings usually think of as a sky. There is a quiet quality to rain that never reaches the ground. It does not roar like a great storm. It does not create dramatic images of thunder, lightning, or flooding water. It takes place silently within the atmosphere, beginning as tiny droplets and ending in evaporation. What remains is not flowing water on the surface, but a process repeating high above. Clouds form, droplets fall, heat causes them to disappear. Vapor and gas continue drifting through the atmosphere. It resembles an unfamiliar chemical breath, a cycle not meant for living creatures, forests, or oceans, but for the hot and heavy planet itself. Thinking about this changes the way we see the light of Venus from Earth. The planet is still beautiful, still resting near the edge of dawn or twilight. But behind that brightness lies a cloud layer, unlike anything in human memory. The beauty does not come from water, but from acid. It does not come from a clear sky, but from the reflection of a thick covering. It does not open into gentle rainfall, but ends with droplets dissolving in the heated air. Venus continues to teach us something slowly. Familiar images in the universe do not always carry familiar meanings. A planet with clouds is not necessarily a wet planet. A bright place is not necessarily a clean one. A sky with falling droplets does not necessarily contain the sound of rain. When ordinary words such as cloud, wind, and rain are placed upon another world, we have to learn them again from the beginning. Venus uses those familiar words to tell a story far stranger than anything on Earth. And beneath that unfinished rain, the surface remains trapped in heat. The rocks are not cooled. The plains receive no droplets from the clouds above. The landers that once rested on the surface of Venus would not have heard rain striking their metal shells. They encountered only a gray-yellow space, hot and heavy, while an acidic sky operated above according to its own rules. The surface and the clouds belong to the same planet, but between them there is no gentle exchange, like water falling and later evaporating again from an ocean. On Venus, the distance between cloud and ground feels like a promise that is never fulfilled. Perhaps this is why the longer Venus is observed, the more unfamiliar it becomes. At first, we see a beautiful point of light. Then that point becomes a sphere of clouds. The clouds open into a dense atmosphere. The atmosphere leads down to overwhelming heat. And now, the clouds become a region of acid where rain never touches the ground. Every new layer of knowledge does not make Venus simpler. It makes the planet deeper, quieter, and more difficult to place within familiar images. A planet with clouds but no gentle rain, with a sky but no clear blue, with light but no familiar life. This is the paradox that makes Venus more alien the longer we look. And once its clouds are understood not only as beauty, but as a chemical curtain, human beings need another way of seeing. Ordinary light cannot penetrate that covering. To learn what truly lies below, we must use different eyes that do not see with visible light, but with radar waves, allowing us to map for the first time the hidden face of Venus. The clouds of Venus do more than make the planet shine. For a very long time, they also kept an important secret hidden from human eyes. In ordinary visible light, the surface below almost completely disappears. We can look at Mars and distinguish different bright and dark regions. We can observe the moon and recognize dark Maria, bright highlands, and craters of many sizes. But when Venus is viewed through a telescope, what appears is not a natural map of mountains and plains. It is a luminous sphere, sealed beneath clouds, smooth and almost entirely unwilling to reveal its true face. This once made Venus a planet of imagination. Before anyone could see beneath the clouds, human beings knew only that a world nearly the size of Earth was there, orbiting closer to the sun, glowing brilliantly in the sky, and always hiding behind a dense veil. That empty space was easily filled with familiar images. Some people imagined that forests, humid swamps, hidden oceans, or a planet resembling the young Earth might exist beneath the clouds. Those ideas were not unreasonable within the knowledge available at the time. When no one could see through the covering, imagination naturally filled the unknown with recognizable landscapes. A planet close to Earth in size and completely wrapped in clouds could easily suggest water, rain, and a protected surface below. But the clouds of Venus were not a partly open door leading toward gentle possibilities. They were a wall of light, beautiful from a distance but almost impossible for human vision to pass through. To discover what truly lay beneath, humanity had to learn another way of seeing, visible light was not enough. It reached the clouds, scattered, reflected, and returned without carrying a clear picture of the ground. Scientists therefore turned to radar. Instead of waiting for sunlight to reflect from the surface, radar actively sends waves downward. These waves can pass through the dense clouds far more effectively than ordinary light. They travel through the atmosphere, strike mountains, plains, slopes, and craters, and then return as echoes. By measuring how long the signals take to return, how strong or weak they are, and how they change, scientists can begin reconstructing the shape of a world that human eyes have never seen clearly. Radar can be imagined as someone feeling an object in the dark. When the eyes cannot see, the hands can still follow its outline. Raised areas, depressions, smooth surfaces, and rough textures gradually become recognizable through touch. Radar performs something similar, but with waves and measurements. It does not see Venus in the way the human eye sees a landscape. It listens for echoes returning from a distant surface and transforms those echoes into a map. The most important moment in this new way of seeing came with NASA's Magellan mission. The spacecraft entered orbit around Venus in the early 1990s, carrying radar designed to map the cloud-covered planet. Instead of attempting to look through the clouds with visible light, Magellan scanned the surface with radar waves, strip by strip, orbit by orbit, region by region. Over time, separate signals were assembled into a broad picture. Venus was no longer only a bright point in the sky or a hot planet described through numbers. It began to possess terrain. There were highlands and lowlands, mountains, plains, volcanic craters, hardened lava flows, and unusual structures unlike anything found in exactly the same form on Earth. This transformed the way humanity understood Venus. Before radar, its surface was like a locked room. We knew the room existed and that it lay directly beyond the door, but we could not see clearly inside. After Magellan, the door did not open in the ordinary sense, but a drawing of the room began to appear. Radar maps revealed that Venus has a complex geological history. Its surface is not smooth and featureless like a simple sphere. It contains broad plains that may be connected to ancient lava, enormous highland regions, countless volcanic structures, and signs that rock once flowed, deformed, and was renewed during the planet's past. The discovery gave the beauty of Venus greater depth. From far away, its clouds make it appear like a shining jewel. Seen more closely, those clouds become acid, moving gas, and a concealing veil. When radar passed through that veil, what lay below was not an empty surface, but a real planet preserving the story of rock. Highland regions may rise like dry, scorching continents. Vast lava plains spread outward like memories of ancient eruptions. Impact craters are scattered across the surface, though not as densely as on the Moon, suggesting that parts of Venus may have been renewed during certain periods of geological history. Every line on the radar map resembles a rough sentence from a book that human beings have only just begun learning to read. Radar maps, however, are not the same as ordinary photographs. They do not show the natural colors of a landscape. Radar images are often processed, colorized, and adjusted to emphasize elevation or surface roughness so that structures become easier to recognize. When we look at these maps, it is important to understand that they are not travel photographs of a distant land. They are the result of returning signals, precise measurements, and scientific methods that transform echoes into images. Even so, these maps allowed Venus to gain a clearer face within the human imagination for the first time. There is something quiet in the act of seeing through beauty. The clouds that made Venus a brilliant symbol of dawn and twilight also confused human understanding. Radar did not destroy that beauty. It only revealed that beauty was not the whole truth. Beneath the smooth brightness lies a surface shaped by powerful processes. Volcanic eruptions, spreading lava, cooling rock, crust stretched or compressed, and impact craters formed and perhaps later buried beneath newer material. Venus has not remained motionless beneath its outward appearance. It has experienced a long geological life, even though that life is very different from Earth's. Thinking about the maps of Venus also reveals the patience required by science. A planet hidden beneath clouds cannot be understood through one hurried glance. Human beings had to send spacecraft, wait for signals, scan region after region, assemble data, correct errors, and compare measurements before a larger picture could gradually emerge. Every line on the map is more than a feature of the terrain. It is also a trace of years of observation, engineering, and curiosity that refused to stop at a bright curtain. Venus became a more specific world through this work. It was no longer only the hot planet or the bright evening star. It had named regions, vast highlands, mountains, enormous lava plains, circular features, long structures, curved formations, fractures, and signs that led scientists to ask how the surface had changed across hundreds of millions of years. Even though no human being could stand there and observe it directly, we could know that beneath the clouds existed real terrain complex, varied, and far from simple. Perhaps this is one of the most beautiful moments in the journey of understanding Venus. The moment when its brilliant outer appearance was replaced by a quiet map. A point of light became a sphere of clouds. The sphere of clouds became a dense atmosphere. The dense atmosphere opened onto a heated surface, and now that surface had form, elevation, flowing rock features, and volcanoes. Each step did not remove the mystery. It simply moved the mystery from, we cannot see anything, to, we can now see, but there is still so much we do not understand. When the curtain of clouds was replaced by radar maps, Venus began telling another story, the story of rock, volcanoes, and a surface that has changed many times. That story leads us deeper into the planet, toward a world shaped not only by heat from above, but perhaps also by heat from within, by lava, by volcanoes that once awakened, and by forces that may not yet have become completely still. When radar maps began to replace the faint brightness of the clouds, Venus was no longer a sealed sphere. Beneath the curtain of acid and heated gas, a rocky face slowly emerged. It was not the gentle face of a planet with oceans, rivers, and green continents. Nor was it a surface densely covered with ancient impact craters like the Moon. Through radar, Venus appeared as a world that had been reshaped many times by heat from within, by molten rock, by vast lava flows, and by volcanic structures scattered across the planet. Across those maps are enormous flat regions. They are not flat in the peaceful way of a field on Earth, but resemble the remains of material that once spread outward and then cooled. Flowing lava can fill depressions, cover older terrain, and create broad plains. Over time, the surface hardens, preserving the shape of a flood of heated rock that passed through long ago. Elsewhere, radar reveals volcanoes of many sizes, unusual rounded domes, and elongated flows resembling scars hardened across the planet's skin. Venus does not allow us to see it directly with ordinary vision, but through radar echoes, its rocks begin telling a story of movement, heat, and a past that was never truly quiet. On Earth, volcanoes are often associated with the boundaries of tectonic plates. Earth's crust is not a single motionless shell of rock. It is divided into large plates that drift extremely slowly over hotter material below. Volcanoes may form where those plates collide, separate, or slide past one another. This explanation is familiar on Earth, but it cannot simply be applied to Venus. Scientists have not found clear evidence that Venus currently has a system of plate tectonics like Earth's. This makes its geological story very different. If heat still needs to escape from the interior, but the crust is not divided into active plates in the familiar way, then the planet must find other paths through which to release its energy. We can imagine the interior of Venus as a place that still retains heat from the time of its formation, along with additional heat produced by natural radioactive processes within the rocks. That energy cannot disappear immediately. It must gradually move outward through the crust through surface deformation, volcanic activity, eruptions, and regions where rock is lifted, stretched, or fractured. On Earth, oceans, the atmosphere, and plate tectonics all participate in a long system of regulation. Venus has no oceans present on its surface. Its atmosphere is extraordinarily dense and hot, and its crust does not display the familiar style of movement found on Earth. Every volcanic structure on a radar map is therefore more than a mountain or a frozen flow. It is evidence that this planet once managed its internal heat in a way of its own. The number of volcanic structures identified on Venus is enormous. Some resemble shield volcanoes on Earth, with broad, gentle slopes formed as lava spreads over large areas. Others are rounded domes, sometimes compared to flattened pancakes, because their lava may have been thicker and unable to travel as far, causing it to swell upward into circular forms. There are also complex regions where fractures, grooves, and lava flows cross one another. Together, these features make Venus appear like a world written in molten rock. But the writing is difficult to read. Radar gives us the outlines, yet understanding when each feature formed, under what conditions, and whether it is still changing requires far more than a single map. For a long time, one of the largest questions was whether Venus remained geologically active or whether all these signs belonged only to the past. A planet with many volcanoes does not necessarily have volcanoes that are active today. The Moon contains ancient lava plains, but it does not experience eruptions like those on modern Earth. Mars has enormous volcanoes, yet most of its volcanic activity lies far in the past. On Venus, the dense atmosphere and unbroken cloud cover make finding new signs much more difficult. We cannot simply look down and see rising smoke or glowing red lava in the way imagination might prefer. Human beings must rely on data, subtle changes, and observations separated by time. What is especially interesting is that some discoveries arrived very late. Magellan collected its data in the early 1990s, but not every secret within that information was understood immediately. Years later, scientists returned to the archive with better tools and new experience and recognized an important sign. A volcanic vent on Venus appeared to have changed shape during 1991. The change did not look like a random detail that could easily be dismissed. It suggested that molten material may have been present, that an eruption may have taken place, or at least that a relatively recent geological disturbance had occurred. A planet once imagined as nothing more than a dead, overheated surface revealed a small movement hidden inside old data. There is something beautiful about this discovery in the particular way science can be beautiful. It was not a fiery volcanic eruption unfolding before human eyes. There was no enormous explosion echoing across a distant planet. There were only preserved radar signals, images of data resting quietly for many years, and then someone looking again with great care and realizing that something had changed. A volcanic vent once had one shape and later appeared different. Beneath the thick atmosphere, below the acidic clouds, on a surface so hot that machinery can barely survive, the rock may still be moving. Venus can therefore no longer be described too easily as a dead planet. This does not mean that the entire planet is erupting violently everywhere. Science always requires caution. One strong piece of evidence does not turn every possibility into an absolute conclusion, but it is enough to change the way we feel about Venus. Instead of seeing it only as a frozen remnant of an ancient climate disaster, we must leave open the possibility that its interior remains active, that parts of its surface may still be renewed, and that volcanoes may belong not only to its past but also to its present. If volcanic activity continues, even rarely or quietly, it would connect with many other parts of the planet's story. Volcanoes can release gases from the interior into the atmosphere. Those gases may affect cloud chemistry, the amount of sulfur dioxide, and the way the atmosphere responds to sunlight. On Earth, volcanoes form part of the long-term carbon cycle. They can be destructive on a local scale while also contributing over immense spans of time to the exchange between rock and atmosphere. On Venus, where there are no surface oceans and no confirmed system of Earth-like plate tectonics, the role of volcanoes may be different, but it cannot be dismissed. The lava plains of Venus are therefore more than terrain. They resemble old pages from a book heated by fire. The strange domes are not merely beautiful shapes on radar maps, but traces of material that once rose from below. Volcanic vents, hardened flows, fractures, and highland regions together form a language of stone. It is a language without sound, but when read carefully, it speaks about heat within the planet, periods when the surface was covered again, and the mechanisms Venus used to release energy while enclosed beneath a dense atmosphere. There is something deeply strange about imagining volcanoes on Venus. On Earth, volcanoes bring images of ash, glowing lava, explosions, evacuations, and later, new land, new islands, and changed landscapes. They are both destructive and creative. On Venus, if a volcano erupts, there are no forests to be covered in ash, no oceans to receive the lava, and no rain to wash the sky clean. Lava would flow across ground that is already intensely hot, beneath an atmosphere that is already crushingly heavy, under murky yellow light unlike Earth's daylight. Such an event could be immense for the planet itself, yet to human beings far away, it might appear only as a small change in data, a mark on a map, or a clue requiring patient interpretation. And because it is so difficult to see, it makes Venus even more mysterious. A planet does not need to display its activity through easily visible scenes. Sometimes it leaves only a very small trace, waiting decades to be recognized. Old data suddenly becomes new. A map that seemed familiar gains another meaning. A volcanic vent that changed during 1991 causes an entire planet to be reconsidered. The old is not truly old, because in science, information can remain silent for a long time before human beings have the right tools and the right questions to hear it. Venus now appears not only as a world heated by its atmosphere, but also as a planet whose interior may not be completely silent. Its clouds make it shine, its atmosphere keeps it hot, and its pressure bears down upon the surface, but the rocks below have a story of their own. Rock once flowed, volcanoes once built the landscape, lava once covered enormous regions, and perhaps somewhere beneath the acidic sky, internal heat is still searching for a path upward. If the volcanoes are still awake, then Venus is not merely the remains of an ancient climate catastrophe. It is still breathing, but through heat, molten rock, and poisonous gases. And that breath leads us toward a deeper question. How can a planet regulate the heat within itself when it has no oceans like Earth, no familiar tectonic plates, and none of the gentler cycles that allow rock, water, and atmosphere to maintain a shared balance? Volcanoes on Venus lead us toward a deeper question about how a planet manages its own internal heat. A rocky world does not receive energy only from the sunday, it also contains heat within itself, preserved from the distant time of its formation, and continually supplemented by quiet processes taking place deep inside the rock. That heat needs a way to escape. The path is not the same on every planet. On some worlds, heat moves outward through fractures, lava, or regions where the crust is being stretched. On others, the surface gradually cools and becomes almost silent. And on some planets, the crust moves so slowly that it shifts only a few centimeters each year. Yet that slow motion can have an enormous influence on climate over long periods of time. Earth is a special example. Beneath our feet, the planet's outer shell is not completely still. It is divided into large plates that move very slowly over hotter material below. Their motion is far too gradual to be felt in everyday life. But across millions of years, it can open oceans, raise mountains, pull continents apart, and create volcanic regions where plates collide or separate. This process is called plate tectonics. Put more simply, Earth's crust is not frozen into one motionless lid. It contains sections that move, collide, sink downward, and are renewed. Plate tectonics does more than create mountains and earthquakes. It also takes part in a much larger story, the regulation of climate. On Earth, carbon does not remain only in the atmosphere. It can enter the oceans, dissolve in water, be used by living organisms, settle onto the seafloor, and gradually become part of the rock. Over very long spans of time, some carbon is stored within the crust. Where tectonic plates sink into the planet, carbon-bearing rock can be carried deep into the interior. Later, volcanoes return some of that carbon to the atmosphere. This journey is extremely slow, far slower than a human lifetime, but it acts like a long-term exchange system among the air, the water, the rocks, and the deep interior of Earth. This does not mean Earth is always perfectly stable. Our planet's history includes periods of intense heat and severe cold, times when ice spread widely, enormous volcanic events that altered the climate, and changes powerful enough to affect life. But Earth has more ways to regulate itself than Venus does. The oceans absorb heat and carbon. Rain helps draw some carbon dioxide from the air into the slow weathering of rock, allowing stone to react gradually with water and gases. Rock stores carbon for long periods. Volcanoes return some of it to the atmosphere. The entire system is slow and imperfect, but together it creates a kind of deep planetary breathing. Venus is different. On its present hot and dry surface, there are no oceans to participate in such a cycle. Acid rain does not reach the ground the way water rain does on Earth. The atmosphere is extremely dense and rich in carbon dioxide, while the surface is heated beneath overwhelming pressure. More importantly, scientists have not found firm evidence that Venus currently possesses active plate tectonics like Earth's. Its surface shows many signs of deformation, fractures, stretched regions, highlands, lava plains, and volcanic structures. But these signs do not form the same clear system of large plates continuously separating, colliding, and sinking as they do on Earth. This difference makes the story of Venus especially important. If a planet's crust behaves like a lid sealed too tightly, internal heat may not escape at a steady rate. It can build over long spans of time and then emerge through volcanic eruptions, regions of surface deformation, or major geological events. Instead of the slow but continuous exchange found on Earth, Venus may have released its heat in a more uneven and extreme way. Scientists are deeply interested in this possibility because a planet's climate depends on more than its distance from the Sunday. It also depends on how the interior exchanges matter and energy with the surface and atmosphere. Imagine Earth as a house with many vents. It is not always comfortable. At times the winds are strong, and temperatures can change unpredictably, but there are still pathways through which air, water, and heat can move. Venus is like another house where many of those outlets have narrowed or disappeared. Its atmosphere holds heat too effectively. The surface lacks water to cool it and take part in reactions with rock. The crust does not show the familiar pattern of plate movement. Under those conditions, heat and gases may remain trapped for longer periods and then be released in less predictable ways. It is also possible that volcanoes and the atmosphere of Venus are closely connected. When volcanoes erupt, they do more than bring lava to the surface. They can also release gases from the planet's interior into the atmosphere. On a world that already possesses such a dense atmosphere, each addition of gas in the past may have contributed to changes in atmospheric chemistry, altered the amount of sulfur dioxide, influenced the acidic clouds, and over very long periods affected the way the planet retained heat. Not every eruption would have caused a major climatic shift, but across millions or hundreds of millions of years, the relationship between molten rock and atmosphere may have become an important part of Venus's fate. Earth also has volcanoes, but Earth has water and a rock atmosphere system that operates differently. When carbon dioxide remains elevated in the air over long periods, rain and weathering can help transfer some of that carbon into rock. This mechanism is extremely slow and cannot correct rapid changes within a human lifetime, but on geological timescales, it contributes to the planet's ability to regulate itself. If Venus lacks oceans and a similar weathering cycle, then it is missing one of the important pathways for removing carbon from the atmosphere. Once carbon dioxide accumulates in large amounts, the atmosphere traps more heat, and the additional warming makes it even harder for water to remain. The parts of the system gradually lock together. When we say that Venus has no easy escape for heat, we are therefore speaking about more than the temperature at the surface. Several pathways are missing at the same time. Energy from the sun enters and is retained by the atmosphere. Heat from the planet's interior may escape through volcanoes, but it is not regulated by a clearly defined system of tectonic plates like Earth's. Carbon dioxide dominates the atmosphere, while water, the substance that could help rocks, air, and the surface participate in gentler cycles, is now almost absent from the ground. A rocky planet can remain active, continue producing volcanoes, and possess complex terrain. Yet, without balancing mechanisms, that activity does not necessarily return it to a more habitable state. This makes Venus a profound lesson in what allows a planet to remain livable. Distance from the sun matters, but it is not enough. A size similar to Earth is not enough. Even having a rocky surface is not enough. For a world to preserve milder conditions over long periods, many parts must work together. A moderate atmosphere, stable water, rocks capable of interacting with the air, an interior that releases heat without becoming too extreme, and cycles durable enough to keep the climate from drifting too far away from balance. Earth possesses this combination in a rare way. Venus shows what can happen when a few parts of that system disappear or function differently. There is a quietness to these processes. Plate tectonics does not make itself known every day. The carbon cycle does not appear before our eyes like a cloud or a rainstorm. Internal heat is not easy to sense while standing on the ground during an ordinary morning. Yet these silent processes have immense power. They determine where mountains rise, which gases enter the atmosphere, how long carbon remains locked in stone, and whether a surface has any opportunity to cool itself. On Venus, the absence or alteration of these mechanisms may be part of the reason the planet remains trapped in its present hot and heavy state. When we return to the radar maps, the lava plains and volcanic structures no longer appear merely as geological forms. They resemble traces of a planet attempting to manage the heat inside itself. Every hardened flow, every dome, and every deformed highland reminds us that Venus is not simply a dead sphere. It has a history, it has an interior, it has its own way of moving. But that movement did not create a world of blue oceans and a gentler climate like Earth. Instead, it contributed to another story, the story of a planet without easy, gradual pathways through which heat and carbon could escape. Venus, therefore, becomes more thought-provoking than the simple image of a burning hell. It is a planetary system that moved away from balance across several layers at once. Its atmosphere became too effective at holding heat. Its surface lost the moderating influence of water. Volcanoes may continue adding gases to the atmosphere. Its crust shows no clear system of plate tectonics like Earth's. These factors do not stand apart from one another. They meet, reinforce one another, and together help shape the fate of this brilliant world. Looking into the history of Venus eventually brings us back to something deeply familiar on Earth but almost absent from Venus today: water. Only a tiny amount remains in the present atmosphere, like a faint trace of something that may once have been far more important. If the distant past of Venus was wetter, if stable bodies of water or even some form of shallow ocean once existed there, then the planet may have passed through a gentler period before being pushed into its present hot and heavy state. To understand how Venus gradually lost its ability to cool and regulate itself, we must follow the story of water, a substance now almost absent, yet one that may unlock one of the greatest secrets of the planet's fate. In the story of Venus, water is like a character that has almost left the stage, yet the traces it left behind continue to draw us back. Today, when we think of this planet, we usually picture acidic clouds, a dense carbon dioxide atmosphere, immense pressure, and a surface so hot that machines can survive there for only a short time. All these images make Venus seem like a world that has never known gentleness, but science does not stop at the form a planet has today. A world may pass through many very different stages before becoming what we now see. And on Venus, the question of water offers one of the deepest paths into that hidden past. Could Venus once have been different from the world it is today? The question does not need to be asked dramatically. It can be considered slowly, like standing before an abandoned old house and wondering how its windows once looked when the lights were still on. Some climate models have suggested that in the distant past, Venus may have experienced conditions milder than those of the present. Its surface may not always have been heated to today's extremes. Liquid water may have existed for some period of time, and some hypotheses have even proposed shallow oceans. But none of this is certain. It remains a possibility under scientific investigation, tested through models, atmospheric data, and the chemical clues that still remain. What makes that possibility so compelling is that Venus is not dramatically different from Earth in size. It is also a rocky planet with a solid body, formed within the inner solar system. Looking only at these basic characteristics, we might imagine that the two worlds once had a better chance of resembling each other. But possibility does not always become destiny. Venus is closer to the Sun and receives more energy. If water once existed on its surface, rising temperatures may have caused it to evaporate more intensely. As water left oceans, lakes, or rocks and entered the atmosphere as vapor, the story would have begun to move in another direction. Water vapor is not merely water in a lighter form. In a planetary climate, it is also a powerful greenhouse gas. On Earth, water vapor contributes to the natural greenhouse effect, helping other gases keep the planet from becoming too cold. But when a system is pushed too far, that same ability to retain heat can make a feedback loop dangerous. Rising temperatures cause more water to evaporate. Additional water vapor in the atmosphere traps more heat. As the planet grows hotter, it becomes increasingly difficult for liquid water to remain stable on the surface. No single step must be violent in the moment, yet across immense spans of time, these changes can gradually pull a planet away from its earlier, gentler state. We might imagine an ancient body of water on Venus, if one ever existed, slowly becoming thinner beneath an increasingly hot sky. It would not disappear in a single day, nor be drained away in one sudden event. Water would rise as vapor and enter an atmosphere that was becoming more effective at holding heat. High above the surface, where sunlight acts more directly, water molecules could be broken apart. Water is made of hydrogen and oxygen. Once those molecules are separated, hydrogen, the lighter component, can escape into space far more easily. Oxygen may take part in other reactions, while hydrogen drifts away, little by little, beyond the planet's gravitational hold. This process would not produce an obvious sight, like a river drying up before our eyes. It takes place high in the atmosphere through interactions among sunlight, water molecules, and space. But given enough time, a small loss can become a great transformation. A planet does not need to lose all its water in a single catastrophe. It can lose it in extremely small steps repeated across millions, hundreds of millions, or even billions of years. Each escaping hydrogen atom is an almost invisible fraction. Yet over sufficient time, those tiny losses may become the memory of an ocean that is no longer there. One important clue lies in the ratio of deuterium to hydrogen in the atmosphere of Venus. Deuterium can be understood simply as a heavier form of hydrogen. Because ordinary hydrogen is lighter, it escapes into space more easily. When a planet loses large amounts of hydrogen over time, more of the lighter form is removed, while deuterium is relatively more likely to remain. A high ratio of deuterium to hydrogen can therefore resemble a trace left behind by a long history of water loss. It does not allow us to look directly back at ancient oceans, but it is like a faded line written into the atmosphere, suggesting that water may once have played a much larger role in the planet's history. Spacecraft such as Venus Express have helped human beings understand that the atmosphere of Venus continues to interact with space, and that light particles can still be lost over time. These measurements do not tell the entire story from beginning to end, but they add more pieces to the larger picture. Venus is not a world isolated from the sun. It has always existed beneath sunlight, the solar wind, and processes capable of changing its atmosphere. If water once evaporated high into the sky, the escape of hydrogen into space may be an important part of the reason the planet is so dry today. Still, caution must remain part of the discussion. Not every study agrees that Venus once possessed stable oceans for an extended period. Some models support the possibility that the planet once had more comfortable conditions. Other research suggests that Venus may have been hot and dry from very early in its history, perhaps never having the opportunity to retain liquid water on its surface in the way Earth did. The differences among these results are not a sign of failure. They show that this is a difficult question, one in which data remain limited, models must continue to be tested, and every hypothesis requires additional observations before it can stand more firmly. That uncertainty is exactly what makes Venus worth continuing to study. If everything were already clear, the planet would be little more than a conclusion in a textbook. But Venus still preserves its areas of shadow. Its clouds hide the ground. Its atmosphere holds chemical secrets. Its surface is observed mainly through radar. Its watery past cannot be seen directly and must instead be traced through models, isotope ratios, atmospheric measurements, and future missions. Every new piece helps us understand more, while also reminding us that Venus has not yet finished telling its story. In a deeper sense, water is more than a liquid. It is part of a planet's ability to regulate and cool itself. On Earth, water absorbs heat, forms rain, weathers rock, carries carbon through long cycles, supports life, and helps prevent the surface from becoming locked into an extreme condition. When water disappears from a rocky planet, many of those regulating pathways weaken with it. There are no longer oceans to absorb heat. There is no water rain to reach the rocks. The familiar circulation among sea, cloud, and land is gone. A planet that loses its water does not merely lose its blue color. It also loses part of its ability to respond gently to heat and atmosphere. The question, where did the water go, is therefore not only about a missing substance. It is about a turning point in the fate of Venus. If water once existed there, how did the planet lose it? If very little water was ever present, what prevented it from appearing in the first place? Both possibilities matter because they help us understand the conditions required for a planet to preserve liquid water. Being rocky, having a size close to Earth's, and lying relatively near the habitable zone do not guarantee that water will remain. A planet needs the right temperature, the right atmosphere, sufficient time, and mechanisms stable enough to keep it from being pushed beyond a distant threshold. Seen from this perspective, Venus is no longer simply a broken Earth or an infernal version of our world. It is a story of how fragile water can be on rocky planets. Water may be present, but its continued existence is never guaranteed. Once the climate enters a cycle of excessive heat retention, water can move from the surface into the atmosphere, and then from the atmosphere into space. That disappearance produces no sound. It does not resemble an ocean visibly withdrawing before us. It is more like a very long breath, during which the lightest parts of the water gradually leave the planet and never return. What makes this story quieter still is that Venus continues to shine. Although it is dry, enclosed in carbon dioxide, and covered by acid rain that never reaches the ground, it still appears before dawn or after sunset as a beautiful point of light. From far away, no one can see the traces of the missing water. No one can hear hydrogen escaping into space. No one can see the hypothetical oceans, if they ever existed. Their story remains only within the data, the models, the ratio of deuterium to hydrogen, and the questions that future spacecraft may help answer more clearly. If Venus once possessed water, then it was not simply born as an inferno. It may preserve the memory of a world that lost the ability to regulate and cool itself. But if Venus became hot and dry very early, that would be equally important, because it would show that a world resembling Earth could still fail to enter a greener path at all. Whichever direction the final answer takes, water remains the key to understanding why Venus diverged from the fate of our planet. And as the traces of water fade almost completely, the story naturally leads toward another form of protection that Earth possesses more clearly. A magnetic field, the invisible shield that helps a planet resist, at least in part, the constant stream of particles flowing outward from the Sunday. As the story of water on Venus gradually unfolds, we begin to see that a planet is shaped by more than what lies upon its surface. Water can evaporate, gases can escape into space, and sunlight can break apart very small molecules high in the atmosphere. All these processes occur along the fragile boundary between a planet and the space surrounding it. At that boundary, Earth possesses a special form of protection that cannot be seen with the naked eye, yet is extraordinarily important. Its magnetic field. Earth's magnetic field is not like a solid wall. It does not block everything completely, nor does it isolate our planet entirely from the Sunday. It can be imagined as an invisible region of influence surrounding Earth, where some of the electrically charged particles arriving from space are deflected. These particles come from the solar wind. Despite its name, the solar wind is not a current of air like the breeze moving through trees on the ground. It is a continuous stream of tiny charged particles flowing outward from the sun into space. Day after day, this stream passes the planets, encounters their atmospheres, affects their upper layers, and leaves its mark on how each world retains or loses its material. Earth has a global magnetic field generated by motion deep within the planet's core. In the outer core, molten metal, primarily iron and nickel, moves under immense pressure and temperature. When electrically conductive material moves within a rotating planet, it can generate a broad magnetic field around that world. The full explanation is far more complex, but in simple terms, Earth's core can be understood as a natural machine quietly creating an invisible magnetic shield. This shield is not merely a distant detail of physics. It contributes to the stability we experience on our planet. When the solar wind reaches Earth, many charged particles are guided around the planet by the magnetic field rather than striking the atmosphere directly. Some energy still enters, particularly near the polar regions, where it can produce auroras. But overall, the magnetic field helps reduce the direct effect of solar particles on the upper atmosphere. In this way, Earth possesses another layer of protection during its very long effort to retain its air and water. Venus does not have a strong, global magnetic field generated internally in the way Earth does. Here, internally generated means produced from within the planet itself, just as Earth creates its magnetic field through the movement of liquid metal in its core. Venus has a core and a rocky body close to Earth in size, but it does not create the kind of powerful magnetic shield that surrounds our planet. The exact reason remains complex. Venus's extremely slow rotation may be related. Its internal structure, the state of its core, and the way heat escapes from the planet may also contribute. The important point is not to enter every individual model, but to recognize that two planets with similar physical bodies possess a major difference in the invisible protection surrounding them. However, saying that Venus lacks a strong magnetic field, like Earth's, does not mean it is completely exposed to the Sunday. When the solar wind encounters the upper atmosphere of Venus, interactions between the charged particles and the gases and plasma around the planet can create an induced magnetic field. Induced means that the field does not originate within the planet's core. Instead, it forms through an external interaction as the solar wind meets the atmosphere and surrounding plasma. It can be imagined gently as water flowing around a stone, producing its own currents and swirling regions. Venus does not have a shield like Earth's, but the collision between the solar wind and its atmosphere still creates a complex region of interaction. This makes Venus more interesting than a planet that is simply unprotected. Its atmosphere is extraordinarily dense. At the surface, the pressure is far greater than it is on Earth. The solar wind, therefore, cannot simply blow once and strip the entire atmosphere away. Venus still retains an enormous envelope of carbon dioxide-rich gas. But high above the surface, where the atmosphere becomes thinner, where lighter molecules can be separated by sunlight or affected by energy from space, the absence of an Earth-like magnetic field may become important over very long spans of time. This is especially relevant to hydrogen, the lightest component of water. When sunlight breaks apart water molecules in the upper atmosphere, hydrogen can escape into space much more easily than heavier elements. If a planet has a strong magnetic field, some of the particles arriving from the sun may be deflected, reducing their direct interaction with the upper atmosphere. If that protection is weaker or operates differently, the loss of light gases may follow another path. Across millions or billions of years, small losses of this kind can contribute to a planet becoming progressively drier. Of course, a magnetic field is not the only answer to the fate of water on Venus. Its closer distance to the sun, powerful greenhouse effect, carbon dioxide-rich atmosphere, the disappearance of any oceans if they once existed, and the behavior of the planet's interior all belong to the larger picture. But the magnetic field helps us understand another layer of the story. A planet does not simply rest beneath sunlight. It is continually touched by particles and energy flowing from its star. A world that preserves an atmosphere and water over immense periods needs more than suitable conditions on its surface. It also needs a sufficiently stable way of interacting with the space around it. Earth is fortunate to possess many layers that support one another. Its magnetic field deflects part of the solar wind. Its atmosphere is thick enough to protect the surface, but not so thick that heat is trapped beyond control. Its oceans absorb heat and participate in both the water cycle and the carbon cycle. Rain weathers rock, gradually drawing some carbon dioxide from the air over very long periods. Plate tectonics carries material downward and later returns part of it through volcanoes. No single layer is perfectly effective, but together they give Earth a system of balance that is more complex, more flexible, and more durable for life. Venus appears to be missing many parts of that system. It has no oceans on its present surface. The familiar water cycle no longer operates. Its atmosphere is too thick and retains heat too strongly. Its crust has not been confirmed to possess Earth-like plate tectonics. And beyond the atmosphere, it lacks a strong, internally generated magnetic field surrounding it like a broad shield. Each factor by itself may not explain the entire fate of Venus, but together, they reveal a planet that has lost many of the pathways through which a rocky world can regulate itself and protect its most fragile materials. There is something deeply thought-provoking about this. A magnetic field is something we almost never experience directly in daily life. When we walk beneath a blue sky, listen to rain, or take a breath, we do not think about liquid metal moving far beneath our feet. We do not think about the solar wind streaming across space, or about charged particles being deflected far above us. Yet these invisible processes still take part in the ordinary peace of the ground beneath us. They are quiet, gradual, and far larger than a human lifetime, which is precisely why they are so easily forgotten. Venus helps us remember those invisible layers. From far away, the planet shines brilliantly, offering almost no sign that it lacks a strong magnetic shield like Earth's. But as we follow the story of its water, atmosphere, and the escape of light particles into space, that difference becomes significant. Venus is not hot only because it lies closer to the sunday. It is not extreme only because it contains so much carbon dioxide. It also shows how a planet exists in a continuous relationship with its star. Sunlight delivers energy. The solar wind carries charged particles. The atmosphere responds. Some material may remain, some may escape, and time transforms very small changes into the history of an entire planet. A magnetic field should therefore not be understood as a magical form of absolute protection. Even Earth loses small amounts of gas into space. Even with a magnetic field, an atmosphere continues to change over time, but the presence of this shield makes Earth's interaction with the Sun different from Venus's. It helps our planet maintain greater stability in the upper atmosphere, while water, rock, clouds, and life below continue participating in long cycles. On Venus, weaker or fundamentally different protection may have added another step along the path toward the dry, hot, carbon dioxide-dense world we see today. Without a shield like Earth's, without oceans remaining on its surface, and without gentle climate cycles, Venus gradually emerges as a lesson in the fragile conditions a world needs to preserve life. But if life is mentioned at all in the story of Venus, it cannot begin on the scorching surface below. It can only be considered very cautiously at higher altitudes, within cloud layers where temperature and pressure are less extreme than at the ground, and where science still leaves open one distant question. From Earth's invisible shield, our journey now rises again into the skies of Venus toward the acidic clouds that not only conceal the planet, but once led human beings to wonder about the most fragile possibility of life. After everything we have explored, the surface of Venus leaves almost no room for gentle ideas about life. The ground is so hot that machines can survive there for only a short time. The pressure is comparable to conditions deep beneath Earth's oceans. The atmosphere is composed mainly of carbon dioxide. No liquid water flows across the rocks. There is no shade and no cool relief when night arrives. If life is understood in the familiar earthly sense, with water, cells, metabolism, and a stable environment, then the surface of Venus appears to have closed that door almost completely. But Venus is more than its surface. Above the heated ground lies an extremely deep atmosphere, divided into many layers that change with altitude. As we rise, the pressure gradually decreases. The temperature also becomes far less severe than it is at the ground. At an altitude of around 50 kilometers, conditions within the clouds include temperatures and pressures that are considerably more moderate than those on the scorching surface below. This region has caused some scientists to pause and look more carefully, not because they have seen forests, oceans, or any clear sign of life, but because on a planet that is almost completely uninhabitable at ground level, the clouds contain a zone where conditions are less extreme. Of course, less extreme does not mean comfortable or easy for life. The clouds of Venus are still acidic. Their tiny droplets contain sulfuric acid, creating a highly corrosive environment. Very little freely available water exists in the atmosphere. The chemistry of the clouds is far removed from the gentler environments found on Earth. When we speak about the possibility of life in the clouds of Venus, our voice must therefore become very measured. This is not a claim. It is only a scientific question being asked in the least hostile region of an extraordinarily hostile planet. On Earth, life has surprised human beings many times. Microorganisms have been found in hot springs, acidic environments, salt lakes, beneath ice, deep inside rock, and near hydrothermal vents on the seafloor, where sunlight never reaches. These tiny organisms are known as extremophiles because they survive under conditions once believed to be too severe for life. They do not need gentle landscapes. They do not require grasslands, forests, or still lakes. Some need only a source of chemical energy, a small amount of water, and conditions stable enough to maintain life on a microscopic scale. The resilience of microorganisms on Earth has made us more cautious when looking at other worlds. If life can survive in hot, acidic, salty, or lightless places on our planet, should we completely dismiss the possibility that it might exist within the clouds of Venus? Science should not answer too quickly. We should not say yes, because there is no convincing evidence, but neither should we close every question simply because the environment is unfamiliar. A more honest approach is to leave a very small opening enough for measurements, hypotheses, and future missions to continue testing the possibility. The cloud layers of Venus therefore occupy a very unusual place in scientific imagination. Below them lies an inferno of heat and pressure. Above them lies space and more intense sunlight. Between these extremes, within a certain range of altitude, temperature, and pressure, may come closer to conditions that machinery and the chemistry of life could tolerate. But the greatest problems remain the acid and the severe lack of water. On Earth, even the microorganisms most tolerant of acidity still require an environment in which their internal molecules are not destroyed. The clouds of Venus are not merely somewhat acidic or slightly harsh. They are so strongly acidic that every hypothesis involving life must overcome many serious barriers. Some research suggests that certain organic molecules may remain stable in concentrated sulfuric acid more successfully than scientists once assumed. This does not prove that life exists in the clouds of Venus. It shows only that chemistry in such an environment may be richer than our first intuition suggested. There is an enormous distance between some molecules can withstand acid and living organisms are present. Science must cross that distance through experiments, observations, and independent verification, not through excitement or a desire for a quick answer. The story received even greater attention when phosphine entered the discussion. Phosphine is a gas that attracted scientific interest because on Earth, it can be associated with certain biological processes in oxygen-poor environments, although it may also be produced in other ways. When researchers reported a possible sign of phosphine in the atmosphere of Venus, many people immediately began wondering about life in the clouds. It was an emotionally powerful moment because Venus had long been regarded as a world almost entirely hostile to life. Even one small atmospheric signal was enough to expand the human imagination. But science does not stop at the first moment of attention. Other research groups re-examined the data, compared the signals, considered whether other gases, such as sulfur dioxide, might have been confused with phosphine, and questioned the certainty of the measurement. The results did not lead to one simple conclusion. Some analyses supported continuing the search for phosphine. Others found no clear evidence. Later observations continued to produce debate. Phosphine on Venus should therefore not be presented as evidence of life. It is better understood as an excellent example of how science works. An unusual signal appears, the scientific community pays attention, and then many researchers test it, challenge it, revise the analysis, repeat the measurements, and wait for better data. What matters most is not reaching the answer yes or no too quickly. What matters is caution. A distant planet cannot be understood through human desire. If we want too strongly to find life, we may turn an uncertain chemical signal into a story much larger than the evidence supports. If we are too eager to dismiss the idea, we may overlook questions worth investigating. Venus requires a more balanced approach, enough curiosity to keep looking, enough discipline to avoid exaggeration, and enough patience to wait for more direct measurements in the future. Within the slow rhythm of this journey, the possibility of life in the clouds of Venus resembles a very small light far away. It is not bright enough to be called a discovery, but it is bright enough to make humanity turn and look again. It does not make the surface of Venus any less extreme. It does not transform the acidic clouds into a gentle home, nor does it change the fact that there is currently no convincing evidence of life on the planet. But it reminds us that even within a world that appears almost completely closed, science may still find another layer in which to ask, measure, and understand more. Perhaps the most appropriate way to view this possibility is as an extremely fragile open question. If life exists in the clouds of Venus, it would not resemble the familiar images people often imagine. It would not be plants, animals, or anything visible to the naked eye. It could only be some form of microscopic organism that, if real, would need to be adapted to intense acidity, scarce water, and highly unusual chemistry. Such a possibility would require exceptionally strong evidence because it would challenge many things we currently understand about life. Until that evidence appears, the most honest position is to keep it where it belongs, as a distant and beautiful hypothesis that has not yet been confirmed. Venus therefore continues to hold two faces at once. One is the hot, dry planet crushed beneath pressure, covered in acidic clouds, and almost entirely uninhabitable at the surface. The other is a natural laboratory for some of the largest questions we can ask. What does life truly require? Where are the limits of organic chemistry? Could a cloud layer ever become a temporary habitat? And how can human beings distinguish a genuine biological signal from a chemical process we do not yet understand? These questions do not make Venus less alien. They make its strangeness more meaningful. Life in the clouds remains only a distant question. Yet unanswered questions are precisely what draw spacecraft back toward this brilliant planet. To understand Venus, humanity cannot remain on Earth and simply watch the bright point appearing before dawn. We need machines that can travel closer, pass through the atmosphere, directly measure the composition of the clouds, listen for faint signals within the dense gases, and return data clear enough to distinguish imagination from unusual chemistry and from the true possibility of life. From that fragile question within the clouds, our journey returns to the spacecraft, the quiet messengers that have repeatedly entered a place human beings still cannot touch. There are places in the solar system that cannot be understood simply by looking at them from far away, and Venus is one of those places. From Earth, the planet appears beautiful. It is bright and steady, sometimes resting quietly before dawn or after sunset, like a small lamp in the sky. But that brilliance reveals nothing of what lies below. Thick clouds conceal nearly the entire surface, and for a very long time, human beings could see only the outward appearance of Venus, while the planet's true face remained behind a veil that was not easy to penetrate. To understand Venus, humanity had to send machines closer. That may sound simple, but it is an enormous challenge. A spacecraft traveling to this planet must cross a great distance, follow the correct path, endure intense heat and a dense, heavy atmosphere, and still manage to send information back to Earth. Here, a signal can be understood simply as a message carried by radio waves, much like a distant device transmitting information to us. At Venus, every message of this kind is precious because the planet is not a place where machinery can survive for long. The first exploration missions were like humanity gently knocking on a locked door. Before it was possible to see beneath the clouds, spacecraft flew past Venus, measuring temperatures, observing the clouds, and studying the atmosphere surrounding the planet. These flybys were extremely brief compared with the lifetime of a world, but they were long enough to transform the way people imagined Venus. Gradually, the idea of a humid and gentle planet hidden beneath the clouds could no longer be sustained. The measurements revealed that behind the beautiful brightness lay a place far hotter, heavier, and more hostile than anyone had expected. After those early flybys, humanity wanted to remain nearby for longer. Some spacecraft were sent to circle Venus repeatedly without landing on the surface, observing the planet from above. This type of spacecraft is usually called an orbiter. It can be imagined as a patient watchman moving again and again around a world, viewing the clouds from many directions, following changes in the atmosphere, and sending pieces of information back to Earth. Thanks to machines like these, Venus was no longer merely a bright sphere. It gradually emerged as a world with moving clouds, an extraordinarily dense atmosphere, and a complicated story hidden behind its brilliant appearance. But the most memorable moments came when human beings attempted to send machines all the way to the ground. In the history of Venus exploration, the Soviet Venera spacecraft hold a very special place. They did not merely fly past the planet or observe it from above. Some of them truly passed through the thick clouds, descended into the hot and heavy atmosphere, and touched the surface. Imagine a small machine beginning its descent through the clouds that make Venus appear so gentle from Earth. The lower it travels, the denser the air around it becomes. Pressure rises from every direction. Pressure is simply the weight of the atmosphere pressing upon everything within it. On Earth, we live beneath atmospheric pressure without usually noticing it. On Venus, however, that pressure is far greater. The descending spacecraft does not encounter heat alone. It is also compressed from every side by the dense gas surrounding it. In such an environment, every part of the spacecraft must struggle to endure. The outer shell has to protect the machinery inside. Scientific instruments must continue working before they fail. Cameras, if they remain operational, must look around and transmit their images in time. Everything happens within a very limited period. Venus gives these machines few opportunities, yet within those brief moments, they still accomplish something extraordinarily important. They allow human beings to see the ground beneath the clouds. Several Venera spacecraft returned images from the surface of Venus. The photographs were not vivid like paintings from science fiction. They showed rocks, gray-yellow ground, dim and heavy light, and an environment so unfamiliar that it was difficult to compare with any landscape on Earth. Yet their simplicity is exactly what makes them so valuable. Humanity no longer had to rely only on guesses about the Venusian surface. A camera had truly stood upon that planet, looked across its heated ground, and sent a few images home. The spacecraft did not survive for long. Even the most durable remained operational on the surface for only a little more than 2 hours. After that, the heat and pressure caused the instruments to fall silent. But before they did, they transmitted things never received before. Every photograph, every measurement, and every faint signal resembled a fragment of a letter arriving from an unwelcoming place. On Earth, human beings received those fragments inside control rooms. On Venus, the small machine remained behind on the scorching ground, beneath a murky yellow sky, surrounded by a world it could no longer endure. Even after reaching the surface of Venus, humanity still wanted to understand the planet on a much larger scale. Venera was the name of the series of probes sent to Venus by the Soviet Union, and several of them truly passed through the dense clouds and reached the ground. The images they returned were invaluable, but they showed only a few small regions of an enormous planet. To learn the shape of the entire Venusian surface, human beings needed a different way of seeing. Ordinary light cannot penetrate the thick clouds well enough to reveal the mountains, plains, or craters below. Scientists therefore used a method similar to sending sound into darkness and listening for the returning echo. But instead of sound, they used waves. These waves traveled through the clouds, struck the ground, and reflected back toward the spacecraft. This way of seeing through returning waves is called radar. Magellan was a NASA spacecraft that orbited Venus during the 1990s and used radar to map the planet's surface. With this method, the clouds were no longer a completely impenetrable wall. Beneath them, broad regions gradually appeared where molten rock had once spread and later hardened, along with highlands, craters, volcanoes, and ancient flows. From that point forward, Venus was no longer only a beautiful but mysterious planet. It became a world with a more clearly defined shape, a turbulent past, and a surface that had been transformed by heat rising from within. After Magellan, other missions continued studying Venus in their own ways. Europe's Venus Express spent years observing the planet's dense atmosphere and cloud layers. It helped human beings learn more about how the clouds move, how Venus retains heat, and why traces of water from its past matter so much. There is no need here to think in difficult formulas. It is enough to remember that Venus cannot be understood only through its surface. The atmosphere surrounding it is also a central part of the story, because it is that atmosphere that makes the planet shine, hides the ground, and traps the heat. Japan's Akatsuki spacecraft continued observing the skies of Venus for many years. It followed the clouds, winds, and changes within the atmosphere surrounding the planet. The story of Akatsuki also carries something deeply human. The mission encountered difficulties when it first reached Venus, yet later found another way to continue its observations. It reminds us that space exploration does not always follow a straight path. Sometimes a mission misses its moment, has to wait, adjust its course, and then receives a second chance. Every machine sent to Venus carries a different purpose. Some observe the clouds, some measure the atmosphere, some attempt to reach the ground, others use waves to map the surface. No single spacecraft can answer every question, but when these separate pieces of information are placed together, humanity gradually gains a clearer understanding of Venus. Some knowledge comes from flybys, some comes from orbiters circling the planet, some comes from landers, some comes from the maps created by Magellan, and still more discoveries appear when scientists return to older data with better tools. What is especially interesting is that old information can still lead to new discoveries. Many years after Magellan completed its mission, scientists continued examining its maps in greater detail. Through this work, they recognized signs suggesting that the surface of Venus may have changed relatively recently on a planetary timescale. A spacecraft may stop operating, but the information it sends home continues to live inside research laboratories. Sometimes an answer does not appear at the moment a signal arrives. It remains quietly within the data for years, waiting for someone to look closely enough. In the future, humanity hopes to return to Venus with new machines. Da Vinci will attempt to descend deep into the planet's atmosphere and make more direct measurements. Veritas will use radar to create clearer maps of the surface. Europe's Envision mission also aims to study both the ground and the atmosphere surrounding Venus. These missions will not merely repeat what has already been done. They will carry more focused questions. How did Venus lose its water? Are its volcanoes still active? And how did its dense atmosphere transform it into the hot and heavy world it is today? There is something deeply admirable in this journey. The machines sent to Venus are tiny compared with the planet they must confront. To survive even briefly, they need power, protective shells strong enough to endure the heat, and a communication link capable of sending information back to Earth. Yet they have crossed immense distances, entered the dense clouds, endured heat and pressure, and still returned fragments of knowledge. Here, data simply means the things their instruments measure: images, temperatures, pressures, or signs detected within the atmosphere. Every signal from Venus is therefore not an easy gift. It is more like an answer that must be won from an extraordinarily hostile place. And because the challenge is so great, every piece of information returned from Venus carries an emotion of its own. Sometimes, it is only a few images of gray-yellow rocks sent by a spacecraft that once reached the ground. Sometimes it is a vast map assembled after many orbits high above the planet. Sometimes it is years of observations following the dense clouds as they move around the world. And ahead, new journeys will continue, carrying the hope of understanding this brilliant yet hidden planet more clearly. Together, all these efforts form one long voyage in which humanity patiently learns to see Venus a little at a time. These machines are not only searching for answers about a distant planet, they are also searching for an answer to a much closer question: what kept Earth from becoming Venus? Each time we look into the dense atmosphere of Venus, we better understand the value of breathable air. Each time radar maps reveal traces of lava, we think more deeply about how a planet releases heat from within. Each time the data reminds us of water that may have been lost, we see more clearly how fragile the oceans of our own world may be. And as new missions continue preparing for their journeys, Venus remains there, shining in the sky like a secret that has not yet come to an end, not only waiting to be explored, but also waiting to help humanity understand its own blue home more deeply. After our journey through the brilliant clouds, the dense atmosphere, the scorching surface, the volcanoes, the vanished water, and the spacecraft sent to explore it, Venus is no longer merely a bright point in the sky. It remains beautiful when seen from Earth, still shining before dawn or after sunset, but that light now carries many more layers of meaning. Within its distant gentleness lies a planet that has reached a climatic extreme, a world revealing just how powerfully an atmosphere can shape the fate of a rocky planet. To describe Venus as a warning does not mean turning it into a direct fear about tomorrow. Earth cannot suddenly become Venus within a short period of time. The two planets have different histories, different amounts of water, different distances from the Sun, and geological and atmospheric systems that are not entirely alike. Venus should therefore not be viewed as a simple picture of Earth's near future. What matters more is the principle the planet reveals. An atmosphere is not a passive background. It can make a world warm enough to support life, or trap heat so effectively that the surface becomes unreachable. On Venus, carbon dioxide became the dominant component of an extremely dense atmosphere. Some sunlight can enter, but the heat released by the surface is retained far too efficiently. Over immense spans of time, this heat-trapping mechanism ceased to be a form of protection and became a trap. Venus is hotter than Mercury, even though Mercury lies closer to the Sun. This shows that distance from the Sun is extremely important, but it is not the only factor determining a planet's temperature. Atmospheric composition, the thickness of the air, clouds, water, rocks, and the way a planet releases heat from within all contribute to the final outcome. Earth also has a greenhouse effect, but in its natural state, it helps our planet retain the warmth it needs. Without this mechanism, Earth would be far colder, and its oceans might not remain as stable as they are today. The difference lies in balance. A moderate amount of retained warmth can support life. Too much heat locked within the atmosphere can push a planet in another direction. Venus is an extreme example of that imbalance. It does not teach us that every greenhouse effect is harmful. It teaches us that a necessary mechanism, when pushed too far, can transform the entire face of a world. What is precious about Earth is that the different parts of its planetary system still interact in many gentler ways. The oceans absorb heat and help distribute energy around the globe. Rain returns water to the ground, slowly weathers rock, and draws some carbon dioxide out of the atmosphere through cycles that unfold over immense periods. Living organisms participate in complex exchanges involving the air, soil, oceans, and carbon. The magnetic field deflects part of the stream of particles arriving from the Sunday beneath the surface. Plate tectonics and volcanoes continue moving material through cycles far longer than any human lifetime. None of these processes works perfectly. Earth has experienced major upheavals. It has warmed and cooled, passed through mass extinctions and ice ages, endured enormous volcanic eruptions, and undergone natural climatic changes. Yet unlike present-day Venus, our planet still retains many pathways through which it can adjust. Water continues to flow. Clouds can still produce rain. Rocks can still store carbon. The atmosphere remains thin enough for the sky to appear blue, yet thick enough to protect life from the direct harshness of space. When placed beside Venus, these ordinary things begin to seem remarkably rare and precious. Venus helps us understand that life needs more than a rocky planet. A solid surface is not enough. A size similar to Earth's is not enough. Even lying near a region that receives a moderate amount of sunlight does not guarantee that everything will follow a gentle path. A habitable planet requires many conditions to coexist over very long periods. Water must not disappear too early. The atmosphere must not trap heat too strongly. Rock and gas need ways to interact. The surface, the planetary interior, and the surrounding space must influence one another at a rhythm that does not destroy the balance too quickly. If life is to emerge and endure, it needs a far more stable stage than the simple image of a rocky sphere orbiting the Sun might suggest. Here, the warning of Venus becomes profound without needing to be loud. It does not speak in a threatening voice. It does not need to become an image of apocalypse. Placing the two planets beside one another is enough to make the lesson clear. On one side is Earth, with blue oceans, rain, forests, breathable air, and a sky that still opens every morning. On the other is Venus, nearly the same size, and also made of rock, yet surrounded by dense carbon dioxide, acidic clouds, and an extremely hot surface. That difference did not arise from a single cause, but from an entire chain of conditions that diverged in opposite directions. By studying Venus, humanity also learns humility before Earth. The things we consider ordinary are not simple at all. Rain falling on a rooftop is the result of a water cycle that still functions. A morning when we can breathe outside is the result of an atmosphere with the right composition. The oceans are not only beautiful, they are enormous reservoirs of heat and carbon. Rocks do not merely lie still beneath our feet. They participate in long cycles that help the planet regulate itself. The blue sky is not merely a color. It is evidence of an atmosphere profoundly different from the murky yellow sky of Venus. Venus also teaches us that climate is an interconnected system, not a collection of isolated parts. Changes in the atmosphere can affect temperature. Temperature affects water. Water influences clouds, rocks, and the ability to store carbon. Volcanoes can release gases into the air. The interior of a planet can shape its surface. The sun provides more than light. It also sends particles and energy outward through the solar wind. A planet always exists within this network of interactions. When the network remains balanced, a world may preserve gentler conditions. When several links begin to shift together, the final state can move very far from where it began. This understanding should not lead to fear. Instead, it can bring a clearer sense of awareness and gratitude. Earth is not precious because it is perfect. It is precious because, within the vast universe, it still preserves so many conditions suitable for life. Water continues flowing through rivers. The atmosphere still lifts clouds into the sky. Rain still reaches the ground. Plants continue exchanging gases with the air. Tiny organisms in soil and oceans still participate in cycles that human beings rarely notice. This planet is not unchanging, but it still possesses the ability to support life in a way Venus no longer does. Venus is therefore more than a distant world to be studied. It is an extreme mirror placed beside Earth. In that mirror, we do not see a direct copy of our future. We see another possible fate for a rocky planet, the possibility of losing water, trapping too much heat, becoming enclosed within a dense atmosphere, and turning into a place where the surface can no longer support life. This comparison does not make Earth seem smaller. It makes Earth feel more extraordinary, not through pride, but through an awareness of its fragility. When we look again at the bright point of Venus in the sky, we are no longer seeing only a beautiful planet. We are seeing a path that Earth has avoided, at least until today. Its light remains gentle and distant, still capable of making the early morning or evening feel more peaceful. But behind that light is a quiet reminder. A world can shine brilliantly and still offer no air to breathe. It can closely resemble us and yet arrive at a very different fate. It can appear beautiful from far away and become extraordinarily hostile up close. And by understanding Venus, we return to Earth with different eyes, moving more slowly, feeling more grateful, and becoming more aware of the balance that keeps our own sky gentle. At the end of this journey, we can return to where everything began, a very quiet stretch of sky, before dawn has fully arrived, or just after twilight has faded beyond the distant rooftops. Against a sky still changing color, Venus remains a familiar point of light. It says nothing. It reveals none of its acidic clouds, crushing pressure, extreme temperatures, volcanoes, or the secrets concealed beneath its dense atmosphere. To the naked eye, the planet is still only a gentle and steady light, beautiful enough to make someone pause for a few seconds without even knowing its name. But now, that point of light is no longer as simple as it was at the beginning. We know that the brilliance of Venus comes from layers of clouds reflecting sunlight. Through scientific imagination, we have traveled through those clouds, descended into an atmosphere as heavy as an ocean of gas, and approached the idea of a surface so hot that machines can survive there for only a short time. We have seen this planet not only through light, but through radar, data, and the machines that once fell through its clouds and returned a few precious images before falling silent. So when we look again at Venus, its beauty has not disappeared. It has simply become deeper. Some forms of beauty in the universe come from splendor that is easy to see. The rings of Saturn, the glowing trail of a comet, or luminous clouds of gas surrounding a young star. The beauty of Venus is stranger. It is beautiful because it conceals, beautiful because it reflects, beautiful because it remains near Earth like a brilliant neighbor, yet becomes more unfamiliar the more we understand it. From far away, the planet seems peaceful, like a small lamp in the sky. Up close, it becomes a world no human being can enter, where the sky is filled with acid, the ground is scorched, and the atmosphere traps heat so efficiently that gentleness has almost nowhere left to exist. What makes Venus memorable is not only its hostility. If it were merely a hot, heavy, and poisonous place, it might astonish us and then cause us to turn away. But Venus holds a greater value. It resembles Earth closely enough to make the differences meaningful. Both are rocky planets. Their sizes are not very far apart. Both formed within the inner solar system. Both receive light from the same sunday. Yet one became a home for oceans, water clouds, and life, while the other became enclosed within dense carbon dioxide, dry heat, and surface conditions where life is nearly impossible. It is the distance between those two fates that makes Venus such a quiet mirror. That mirror does not need to frighten us. It simply reminds us that a habitable planet is not something guaranteed. Earth is not precious because it lies at the center of the universe. It is precious because, among so many conditions that could have moved in another direction, many things have maintained a workable balance for long enough. The air remains suitable for breathing. Water still moves through rivers, oceans, rain, and clouds. Rocks continue participating in cycles longer than a human lifetime. The magnetic field quietly deflects part of the particle stream coming from the sunday. Living things, from forests to microscopic plankton, continue influencing the atmosphere in subtle ways. These conditions often seem ordinary only because we live among them every day. Venus allows us to see those ordinary things with different eyes. Rain on Earth is no longer merely weather. It is evidence that an active water cycle still exists. A morning when we can open a door and breathe the outside air is evidence of an atmosphere that is neither too thin nor too thick, and not locked within extreme heat. A white cloud drifting across the sky is not only beautiful, it is profoundly different from the acidic clouds surrounding our brilliant neighbor. Once we know that Venus has clouds, but that its rain never reaches the ground, we hear the sound of rain on Earth with a deeper sense of gratitude. Perhaps this is the final beauty that Venus leaves with us. It is not the beauty of a place where we wish to stand. It is not the beauty of a world that could become a home. It is the beauty of a reminder. Venus reminds us that climates have histories. Atmospheres have power. Water can be lost. A rocky planet without the necessary balancing mechanisms can move so far from gentler conditions that returning becomes extraordinarily difficult. These lessons do not arrive as a loud warning. They rest quietly within the light of a planet appearing in the early morning or late evening, waiting for human beings to become curious enough to understand. The spacecraft sent to Venus have also become a beautiful part of this story. They are tiny compared with the planet they approach, yet they carry human patience with them. Some flew past and measured the atmosphere. Some entered orbit to study the clouds and heat. Some used radar to map the hidden surface. A few landers reached the scorching ground, sent back several images, and then fell silent forever. Their signals are like fragments of letters sent from an immensely distant and hostile place, with each fragment making the picture of Venus a little clearer. Venus still holds many unanswered questions. The history of its water is not fully understood. Its volcanoes may still be active. The chemistry within its clouds requires more direct measurements. The question of life in those clouds remains distant, fragile, and unsupported by convincing evidence. Yet these unknowns are precisely what continue drawing human attention toward the planet. A world that cannot be touched by the human body can still be reached through questions, instruments, data, and careful imagination. At this point, we no longer need to see Venus as a world containing only darkness behind its beauty. It is better understood as a paradox. It shines because of its clouds. It is beautiful because it reflects light. It feels close because it is our planetary neighbor. It remains distant because the environment beneath those clouds is so hostile. It resembles Earth in several fundamental ways, yet differs enough to become one of the deepest lessons about the paths a planet can follow. Within that paradox, Venus loses none of its brilliance. Instead, its brilliance gains depth, like a light carrying the memory of atmosphere, rock, heat, and time. In the end, all these thoughts bring us back to Earth, not with pride, but with a quieter spirit. Here, air can still enter our lungs. Water can rest inside a glass, flow beneath a bridge, fall upon a rooftop, or remain quietly within the ocean. Clouds can shade the ground and then dissolve. Morning continues to arrive in its familiar way, so gently that we sometimes forget this familiarity is a gift. When Earth is placed beside Venus, even the smallest details of daily life begin to carry a different value. And as the night grows deeper, that point of light remains there, quietly beside Earth. It does not draw us toward fear. It simply stands in the distance as a calm reminder that the universe contains many forms of beauty, but not every beautiful place can be touched. Some brilliant worlds can only be observed, studied, and respected from very far away. And sometimes, the most precious place is the one so familiar that we forget to notice it. A place where we can breathe, listen to rain, watch clouds drift, and peacefully close our eyes beneath a sky